3 days ago, an asteroid passed between this planet and the Moon. It came within 249,000 kilometers of the ground beneath your feet. Nobody on Earth knew that rock existed until roughly 1 day before it arrived. It was never going to hit us, and that is not the interesting part. The interesting part is that we found it with a single day to spare. The same blind spot hid the rock that exploded over Chelyabinsk in 2013. That airburst injured roughly 1,500 people with no warning at all. So here is the question this entire story turns on, and it stays open. How many rocks big enough to erase a city are uncatalogued right now? If that question grips you, subscribe now and comment below where you are watching from. Let's get into it, starting with the object that slipped past us on Monday. Part 1. The rock that arrived 1 day after we noticed it. The object is called 202060X3, and it is an Apollo-class asteroid. That classification tells you something specific about the shape of its orbit around the Sun. Apollo objects sit farther from the Sun than we do on average. Their orbits are stretched enough that they cut across the lane where Earth travels. Picture a runner on a wide oval track who occasionally swings inside your lane. That is the geometry, and roughly 2/3 of known near-Earth asteroids share it. Its semi-major axis is 1.34 astronomical units, so it averages about 1/3 farther from the Sun than we do. Its eccentricity is 0.308, which is a meaningful figure. That number means the orbit is noticeably stretched rather than round. Its inclination is 11.5 degrees, tilting it slightly out of the plane the planets share. One full lap around the Sun takes it 566 days to complete. Now here is the number that made me stop and read the entry twice. The minimum distance between its orbital path and ours is remarkably small. That figure is 0.000868 astronomical units. In plain terms, the two tracks come within about 130,000 kilometers of touching. That is roughly 1/3 of the distance between here and the Moon. The paths themselves nearly intersect, permanently. Regardless of where either object sits today, I want to be careful about what that does and does not mean for you. Two racetracks can nearly overlap for 10,000 years without the runners ever colliding. The paths crossing is a necessary condition for an impact, not a sufficient one. What it does mean is that this object stays on the watch list forever. The geometry is already in place, and only the timing separates a flyby from something else. Hold that distinction, because it governs how every object in this story gets assessed. Astronomers are rarely asking whether a rock could hit us in principle. They are asking whether the timing works out inside a window we can actually calculate. So let me give you the timing on this one. Precisely, the first recorded observation of 2026 OX3 came on the 26th of July. Its closest approach happened at 1843 Universal Time on the 27th. That is a gap of roughly 36 hours between discovery and closest approach. The object measures somewhere between 10 and 23 meters across, based on its brightness. It was moving at 9.45 kilometers per second relative to Earth. In more familiar units, that is a little over 21,000 miles per hour. A commercial airliner cruises at roughly 600 miles per hour for comparison. At 10 to 23 meters, this rock posed no threat to any city on this planet. If it had entered the atmosphere, it would have produced a bright fireball and a loud bang. Windows underneath might have cracked if the geometry was unlucky and the entry angle steep. Meteorite hunters would have spent a pleasant week searching fields for fragments. That is genuinely the extent of what a rock this size does to us. I am telling you that up front for one specific reason here. The size of this rock is a coincidence, and the timeline is not. The 36-hour warning was not a function of how dangerous this particular rock happened to be. It was a function of where the rock came from and how bright it appeared. That same detection process applies identically to an object 5 times wider. Let me put a marker down that the rest of this story keeps returning to. Our warning time depends on the geometry of the approach, not on the danger of the object. Those two things are completely uncoupled, and that is the uncomfortable fact underneath everything. There is one more figure attached to this asteroid that deserves your attention. Astronomers assign newly found objects a condition code running from 0 to 9. 0 means the orbit is nailed down and the object can be found again easily. Take note of this scale, because it recurs throughout the whole story. 9 means the orbit is so uncertain that recovering the object may prove impossible. 2026 OX3 carries a condition code of 7 on that scale. 7 is a high number, and it reflects an observation arc of about 1 day. We saw it, we watched it for hours, we calculated where it was going. Then it receded into the dark and became substantially harder to find again. That is not sloppiness on the part of anyone involved in the process. It is the arithmetic of short observation arcs, and it happens dozens of times a month, but it means our knowledge of this object is provisional in a way most people never consider. Let me give you a sense of what that discovery night actually looked like. A survey camera recorded a faint smear of light moving against fixed stars. Software flagged it automatically, because no human is watching those images in real time. The detection went to the Minor Planet Center, which assigns designations and computes preliminary orbits. Other observatories were alerted so they could confirm the object and extend the arc. That whole chain, from first photon to catalogued object, can complete within hours. It is genuinely impressive engineering, built up over 3 decades of refinement, and it began roughly 36 hours before the rock reached its closest point. David Farnokia, a navigation engineer at the Jet Propulsion Laboratory, has described these events plainly. He has said that close approaches happen all the time around this planet. They are simply part of the fabric of the solar system. That is accurate, and it is the correct professional framing for an object like this. But I want to hold the phrase inside the orbit of the moon steady for a moment. That distance sounds enormous, and by everyday standards it obviously is. 249,000 kilometers would take a commercial airliner around 3 weeks to cover. Against orbital distances, though, that figure is uncomfortably tight, rather than reassuring. The moon itself sits at 384,000 kilometers on average. Every satellite that humanity currently operates orbits far closer to us than that. So an object passing at 249,000 kilometers has entered our immediate neighborhood. More importantly, that distance says nothing about how close it came to hitting us. Distance in space is not the same as distance in the timeline. Earth moves along its orbit at roughly 30 kilometers per second. It covers 249,000 kilometers of its own path in about 2 hours. Let me put that plainly, because it changes how you should read every Flyby figure. A miss of 249,000 kilometers is a miss of roughly 2 hours. Shift the object's arrival by that much, and the geometry looks very different. Now, that shift did not remotely threaten to happen with this rock. Its orbit was calculated, and the miss was never in question once observed. Orbital mechanics is deterministic, and 2 hours of timing error is astronomically large. I raise it because it reframes what these numbers mean when you hear them. When an agency reports a pass at half a lunar distance, you hear a distance. What the physics is describing is a near coincidence in timing across millions of years. 2026 OX3 was not alone in the sky last week. It was not even the closest object to pass us in that stretch. 2 days earlier, something came nearer still, and almost nobody wrote a word about it. Part 2. 8 visitors in 9 days, and the one that mattered most. Between the 24th of July and the 1st of August, NASA logged a series of close approaches. Individually, each one is unremarkable, and none of them threatened anyone. Taken as a group, they describe the actual traffic conditions around this planet. On the 24th of July, 2026 KU-3 passed this planet. Its closest approach came at 1:31 in the morning Universal Time. Its distance was 2,950,000 kilometers, or 7.68 lunar distances. One lunar distance is the average gap to the Moon, roughly 384,000 kilometers. Its absolute magnitude is 23.24, which implies a size range. That range runs from 60 meters up to 135 meters. Hold that size range in your head for the next 2 hours. I will keep returning to it, because it defines this entire subject. 60 to 135 meters is the range that keeps planetary defense people awake at night. The 25th of July was a busy day by any standard. 2026 OC3 passed at 1,107,000 kilometers. 2026 OD is a separate object, despite the confusing similarity. It passed at 1,775,000 kilometers from Earth. That one is estimated at between 56 and 125 meters across. Then came 2026 OD3, which is the closest pass of the entire week. It came within 228,000 kilometers, which is 0.59 lunar distances. That is comfortably inside the Moon's orbit, and it received essentially no coverage anywhere. Later that same day, 2026 OB1 passed at 867,000 kilometers. It was moving at 22.43 kilometers per second, the fastest object of the week. On the 27th, 2026 OA3 passed at 1,891,000 kilometers. 14 hours after that, 2026 OX3 threaded inside the lunar orbit. Tomorrow, on the 1st of August, 2026 OS makes its approach. It will pass at roughly 3 lunar distances from this planet. That last one carries a caveat that is worth stating plainly here. Its observation arc is so short that the arrival time is uncertain by about 21 hours. The distance itself could plausibly land anywhere inside a fairly wide range. That range runs from 2.87 to 3.27 lunar distances. We are not really tracking that object so much as estimating where it probably is. It is worth explaining what that logging process involves, because it is continuous. I want you to picture the scale of this record before the details. NASA's Center for Near-Earth Object Studies maintains a close approach database. Every catalogued object with a calculated orbit appears there automatically. The database projects forward and lists everything passing within specified distances. That system runs without human intervention for the routine cases. Nobody decides whether a given flyby is newsworthy or alarming. The orbit is computed, the approach is listed, and entries update as observations arrive. Roughly 2,000 objects pass within a few million kilometers each year. Several dozen pass inside the orbit of the Moon annually. A handful of them pass closer than the geostationary satellite ring each year. Those numbers have climbed steadily for 20 years, tracking telescope capability precisely. In the 1990s, discoveries ran at a few hundred objects per year. The current rate exceeds 3,000 new near-Earth objects annually. That is 8 objects logged in a span of 9 days. 2 of them passed inside the orbit of the Moon. 2 of them fall in the size class that could level a metropolitan area. Now I need to address the question that this list always provokes. I am going to answer it honestly rather than dramatically. Is the traffic increasing, and is the population out there genuinely changing? Has the sky become more dangerous than it was a century ago? The answer to all of that is no, and I want to say it plainly. The traffic is not increasing, and I want to be direct about that. I would rather say so than sell you a trend that does not exist. What has changed dramatically is the number of telescopes systematically photographing the night sky. 20 years ago, a week like this would have produced maybe one detection, possibly none. The near-Earth environment has always been exactly this busy. Objects in this size range pass within a few lunar distances constantly, many times per week. They have done so continuously for the entire history of this planet. That history runs to 4.5 billion years of constant traffic. We are not watching an escalation in the sky above us. We are watching an escalation in our own capacity to notice. I need you to hold on to that distinction, because it changes what the correct response is. A rising threat demands urgency and emergency funding and immediate action. A static threat with an incomplete map demands something much harder to sustain politically. It demands patient, boring, decades-long investment in instruments that mostly find nothing. Those two situations feel identical from inside the news cycle. Confusing them wrecks nearly every public conversation about this subject. So the sky above us has not changed in any meaningful way. Our eyes have improved from nearly blind to substantially incomplete. That is genuine progress, achieved on small budgets by a small number of people. It is also nowhere near sufficient, and I can show you exactly how insufficient using official figures. I want to explain why every size figure in this story comes as a range. It is not vagueness on my part, and it is not sloppy reporting. What a telescope actually measures is brightness, and never size directly. Specifically, it measures absolute magnitude, a standardized figure written as H. That number tells you how bright the object would appear at a defined distance. To convert brightness into diameter, you need to know how reflective the surface is. Astronomers call that reflectivity albedo, and it varies enormously across asteroids. Some are bright, reflecting a quarter of the light that strikes them. Others are darker than fresh asphalt, reflecting only a few %. So a given brightness is consistent with a small pale rock or a large dark one. The difference between those two interpretations can be a factor of 3 in diameter. And because mass scales with the cube of diameter, that is a factor of 27 in mass. Hold that number, because it is the same 27 from the scaling I described later. Our uncertainty in a typical size estimate spans the entire gap between nuisance and catastrophe. This is precisely why infrared observation matters so much for this work. Follow this next step carefully, because it decides everything downstream. Infrared measures emitted heat, which depends on surface area rather than reflectivity. A dark asteroid absorbs more sunlight, so it runs hotter and glows brighter in infrared. The two effects nearly cancel, which makes infrared size estimates far more reliable. That single fact drives the design of the most important instrument in this story. I will return to it, and it explains why the solution has to leave the ground. For now, apply this to the week's traffic, and the picture sharpens. 2020 6KU3 has an absolute magnitude of 23.24. That single measurement is consistent with 60 meters or with 135. 60 meters is Tunguska, and 135 meters is a regional catastrophe. We do not know which one passed us 6 days ago. Nobody pointed an infrared telescope at it because there was no reason to. It was never going to hit anything, and telescope time is scarce and contested. That is the ordinary state of knowledge about ordinary objects. We know roughly where they are, and we know their brightness precisely. We know their actual size within a factor of 2, and often worse. But before those numbers mean anything, you need to understand how a rock gets found, because the method has a flaw built into it at the level of physics itself. Part 3. Why the only way to find a rock is to watch it move. There is a picture most people carry of how asteroids get discovered. An astronomer at an eyepiece notices a point of light that should not be there. That has not been how this works for several decades now. Modern asteroid discovery is a statistical operation performed by software on enormous volumes of data. A survey telescope photographs a patch of sky and records everything in it. A few minutes later, it photographs the identical patch again. Then it repeats that process a third and fourth time. Software subtracts each image from the next and searches for anything that shifted position. Stars do not shift measurably between exposures taken minutes apart. Distant galaxies certainly do not shift position on those short timescales. A rock at a few 100,000 kilometers crosses visible distance in minutes. That motion is the entire signature, and it is the only signature available. Think of it as spotting a fly in a photograph of a wall covered in nails. In a single image, the fly and the nails look identical to any algorithm. Take a second photograph, and only one of them has moved. That comparison is the whole discovery technique, from the smallest survey to the largest. 4 facilities perform most of this work, and each has a distinct role. The Catalina Sky Survey operates from Mount Lemmon and the Bock Telescope near Tucson, Arizona. Learn these 4 names, because everything else depends on them. NASA funds it directly, and it has been among the most productive discovery programs ever built. In October of 2025, Catalina detected an object called 2025 TF. That detection came hours after the rock had already skimmed past Antarctica. Pan-STARRS operates from Haleakala on the island of Maui in Hawaii. It sits above much of the atmosphere, where the sky is exceptionally dark and steady. It discovered the fast-spinning object I will describe much later in this story. The design targets for that system are worth stating, because they set expectations honestly. It was specified to provide roughly 1 day of warning for a small object. For something in the 30-meter range, the target was around a week. For a larger object approaching 140 meters, several weeks. Those are modest numbers by any standard, and they were chosen deliberately. The system was never intended to find objects years in advance. It was built to catch what the deeper surveys missed on final approach. 1 day of warning is enough to issue a public advisory about windows. 1 week is enough to consider limited evacuation of a predicted impact zone. Several weeks is enough to plan a response, though not to build a spacecraft. That is the philosophy behind a last alert system, and it is realistic rather than ambitious. Atlas was built for a fundamentally different purpose than the other surveys. The name stands for Asteroid Terrestrial Impact Last Alert System. That word last is not decorative, and it tells you the design philosophy. The Atlas network spreads telescopes across Hawaii, Chile, and South Africa. It sweeps the entire visible sky repeatedly on a short cadence, hunting objects already on final approach. An Atlas unit in Rio Hurtado, Chile, found the most consequential asteroid of this decade. The Zwicky Transient Facility at Palomar Observatory in California adds another wide-field survey to the network. It photographs enormous swaths of sky nightly, and asteroids are only part of what it hunts. And then there is the newest instrument, which is genuinely reshaping this entire field. The Vera Rubin Observatory in Chile released its first substantial dataset recently. Inside that single release were roughly 2,000 previously unknown asteroids. 2,000 objects from early data from one facility in one release. Rubin matters for a reason, beyond raw discovery numbers, and it is worth understanding. It returns to the same patches of sky repeatedly on a planned schedule. That repetition is exactly what converts a detection into a secure orbit. The chronic problem in this field has never been finding things once. The problem is finding them again before the uncertainty grows too large. Let me give the people who built this network their full due here. They assembled it on modest budgets against long stretches of institutional indifference. It finds thousands of objects a year that nobody knew existed. It works, and it works measurably better with each passing year. Now let me tell you what it structurally cannot do, no matter the funding. Every telescope I have just named sits on the ground beneath the atmosphere. Every one of them requires darkness in order to operate at all, which means every one of them, by definition, points away from the sun. Sit with the geometry of that for a moment, because it is the crux of this story. You are standing on a rotating ball on the night side, staring outward into darkness. On the other side of the planet sits a star of overwhelming brightness. Its scattered light in our atmosphere makes astronomical observation impossible for half of every rotation. Any object approaching Earth from the direction of the sun arrives through unwatchable sky. Not poorly watched sky, or occasionally watched sky, but sky no ground telescope can examine. That is the sunward blind spot, and it is not a funding problem or an engineering oversight. It is the atmosphere doing precisely what atmospheres do to incoming light. Sunlight scatters off air molecules and turns the daytime sky into a glowing sheet. A faint moving rock against that sheet is not merely hard to detect. It is invisible the way a candle is invisible in front of a searchlight. Remember that candle, because I will bring it back when the physics gets worse. And it does get worse from here, in one specific way. The second problem compounds the first, rather than merely adding to it. There is a second structural blind spot that receives far less attention than the solar one. It has nothing to do with brightness and everything to do with perspective. Consider what an object on a collision course actually looks like from the target. It does not sweep across your sky the way a passing rock does. It sits in nearly the same position, growing steadily brighter night after night. The apparent motion approaches zero precisely because the object is aimed at you. Now recall that Discovery software works exclusively by detecting change in position. An object that barely moves between exposures produces the weakest possible signal for that software. It looks like a faint star that happens to be slowly brightening. Let me state that plainly, because it is the most counterintuitive fact in this discipline. The more precisely an asteroid is aimed at you, the less it appears to move. The less it appears to move, the harder your detection system finds it to see. That is not a bug in anyone's code, and no amount of clever programming eliminates it. It is a consequence of viewing three-dimensional motion from a single fixed vantage point. You cannot see the depth component of motion from one location, ever. Both blind spots have the same solution. And the field has known what it is for decades. You need a second vantage point, positioned somewhere other than the surface of Earth, preferably somewhere sunward, and preferably observing in wavelengths the atmosphere blocks entirely. That instrument exists on paper, it is being assembled right now, and it is not in space. I will tell you exactly where it is and when it flies, but not yet. There is one more constraint on this network that people rarely think about. Sky coverage is a scheduling problem, and the arithmetic is unforgiving. The entire celestial sphere covers roughly 1,000 square degrees. Only about half of that is above the horizon at any given moment. A survey camera might image several square degrees in a single exposure. To cover the accessible sky once, you need thousands of pointings. Each pointing must be repeated at least 3 or 4 times to detect motion, so a full sweep of the observable sky takes multiple nights of perfect conditions. And perfect conditions are the exception, rather than the rule at any site. Count the obstacles along with me as I list them out. Weather closes observatories regularly, sometimes for weeks in the wrong season. The moon washes out faint objects for roughly a third of every month. Near full moon, the limiting magnitude at even excellent sites degrades substantially. Faint asteroids simply drop out of the accessible population for those nights. Now stack all of those constraints together, and an uncomfortable picture emerges. Any given patch of sky is genuinely surveyed only a fraction of the time. An object can cross an unwatched patch and be gone before anyone looks there. This is why the same object is often found independently by several surveys. It is also why plenty of objects are found by nobody at all. I want you to notice how ordinary these limitations are. There is no conspiracy, no negligence, and no hidden competence being withheld. There are a limited number of telescopes, a limited number of clear nights, and an enormous sky. Let me anchor that with a number that puts the effort in perspective. The entire ground-based near-Earth object observation program runs on a modest budget. It received $41 million in fiscal year 2025. That is the total United States funding for finding the objects that could destroy a city. $41 million is roughly the production budget of a mid-sized film. It funds telescope operations, staff, data processing, and follow-up across multiple facilities. And it has produced the discovery of tens of thousands of objects. I am not offering that as outrage. And I am not telling you what to conclude. I am placing the number beside the task so you can size the effort yourself. First, I need to take you to a Russian city on a February morning, because everything I have just described stops being theoretical there and starts having a casualty count. Part 4. The morning the light arrived 2 minutes before the sound. On the 15th of February 2013, an object entered our atmosphere. The time was roughly 9:17 in the morning, local time. It measured between 17 and 20 meters in diameter, based on later analysis. It was travelling at approximately 18 to 19 kilometers per second when it arrived. Its path took it over the Ural region of Russia, near the city of Chelyabinsk. Let me convert that velocity into something your body can understand. 18 kilometers per second is roughly 68,000 kilometers per hour. It is around 50 times the muzzle velocity of a rifle bullet. At that speed, you would cross the Atlantic Ocean in under an hour and a half. Now I want to correct something that almost everyone believes about atmospheric entry. The rock did not burn up from friction with the air. Friction is the common explanation, and it is essentially wrong. What actually destroys these objects is compression, and the difference matters enormously. The object was moving vastly faster than sound travels through air. That means the atmosphere ahead of it had no time to flow around it. Slow down here, because this is where the physics stops being intuitive. Air cannot get out of the way of something moving at 18 kilometers per second, so the air gets crushed instead, violently and almost instantaneously. When you compress a gas that hard and that fast, it heats. The air in front of the rock reached temperatures of thousands of degrees, not from rubbing against the surface, but from being slammed into a wall. That superheated compressed air is what tears the object apart. Here is why the rock loses that fight, and it comes down to internal structure. Most asteroids in this size class are not competent solid stone. They are fractured throughout, carrying cracks and voids from billions of years of collisions. The pressure on the leading face reaches dozens of atmospheres at those speeds. That pressure finds every existing crack and drives itself in. The rock does not melt in any meaningful sense of that word. It comes apart along the internal flaws it was already carrying. And once it begins coming apart, the whole process cascades violently. Fragments present far more total surface area to the oncoming air than the original body did. More surface area means far more drag, which means far more rapid deceleration. Rapid deceleration means the kinetic energy dumps into the atmosphere in a fraction of a second. That runaway disintegration is the process we describe as an airburst. Over Chelyabinsk, it released energy equivalent to a very large detonation. The figure was between 440 and 530 kilotons of TNT. The detonation happened at an altitude between 23 and 30 kilometers above the ground. That number needs context, or it means nothing to you. The weapon dropped on Hiroshima in 1945 released approximately 15 kilotons. The Chelyabinsk airburst was therefore roughly 30 times that energy release. It happened above a populated Russian city on an ordinary Friday morning. The flash was briefly around 30 times brighter than the sun in the sky. People across the region stopped what they were doing and looked up. Many of them walked to their windows to see what was happening. That detail is the entire tragedy of Chelyabinsk, and I will return to it. Then, the shockwave arrived, and it did not arrive immediately. It took roughly 2 minutes to descend those 20-some kilometers to street level. In those 2 minutes, thousands of people had positioned themselves directly in front of glass. 1,491 people were injured that morning. Approximately 7,200 buildings across 6 cities sustained structural damage. Nobody died that morning, which is remarkable given the figures involved. Now here is the detail that reframes the entire event, and I need you to hold it. Almost every single injury was caused by flying window glass, not by heat, not by fire, not by fragments of the rock itself, by ordinary glass blown inward by the pressure wave into people's faces. They were at the windows because they had seen a bright light and gone to look. The most natural human reaction imaginable put 1,500 people in the path of that glass. I said nobody died, and that is true, and it was substantially luck. The object arrived at a shallow angle over a region of relatively low population density. It detonated high, spreading the pressure wave over a wide area rather than concentrating it. A steeper entry over a denser city would have produced a very different casualty list. Now consider the size of that object against the rock from Monday. Chelyabinsk was 17 to 20 meters across, by the best estimates. 2026 OX3 was 10 to 23 meters. Those two size ranges overlap across most of their extent, and the warning time for Chelyabinsk was not 36 hours. It was not 1 hour, and it was not 1 minute either. The warning time for Chelyabinsk was 0, in the most literal sense. Not a single telescope on this planet detected that object before it entered the atmosphere. The first indication that it existed was the flash in the sky. 1,500 injuries, 7,000 damaged buildings, and complete surprise. The reason for that surprise is the thing I described in the previous part. The Chelyabinsk object approached from the direction of the sun. It came in through the cone of unwatchable sky, invisible as a candle before a searchlight. There is a physical object from that morning you can go and look at. It sits in a museum in Chelyabinsk, and it weighs about 650 kilograms. The largest recovered fragment of the object punched through the ice of Lake Chelyabinsk. It left a hole roughly 8 meters across in the frozen surface. Divers recovered it from the lake bed in October of 2013, 8 months later. When they lifted it onto a scale, the fragment broke into pieces and the scale failed. That single stone is what remained of a body weighing perhaps 12,000 tons. Nearly everything else was converted into light, heat and pressure in the upper atmosphere. The atmosphere did its job, and it did it violently, which is worth stating clearly because it is the reassuring half of this story. Our atmosphere is an extraordinarily effective shield against small impactors. It stops essentially everything below 10 meters before it reaches the ground. Give this next point a moment, because it cuts both ways. For objects up to a few tens of meters, it converts the impact into an airburst. Think of the atmosphere as a 100-kilometer thick cushion above your head. Anything arriving fast enough gets crushed against that cushion rather than through it. The cushion is why this planet's surface is not covered in small craters. But that same cushion is what turns a rock into an area weapon. A solid object hitting the ground damages the ground it hits. An airburst distributes its energy as a pressure wave across an entire region. Now, the injuries at Chelyabinsk followed a distribution that tells its own story. Emergency services across the region reported over 1,000 people seeking treatment within hours. The overwhelming majority presented with lacerations from glass rather than burns or trauma. Roughly 100 people were hospitalized, and 2 were reported in serious condition. Schools were in session that morning, which could have made the outcome far worse. In several buildings, teachers had time to move students away from windows. In others, the glass came inward before anyone understood what the light had been. Remember the 2-minute gap between the flash and the shockwave? That interval is the entire margin between an ordinary morning and a mass casualty event. Everything about the human cost of that day lived inside those 2 minutes. There is a global sensor network that heard that explosion, and it was not astronomical. The Comprehensive Nuclear Test Ban Treaty Organization operates infrasound stations worldwide. They listen for very low-frequency pressure waves traveling through the atmosphere. Those stations exist to detect clandestine nuclear tests anywhere on the planet. They also detect large airbursts, because the two produce similar acoustic signatures. The Chelyabinsk event registered on stations thousands of kilometers away. Some detections came from more than 15,000 kilometers from the entry point. The infrasound waves circled the planet more than once before dissipating. That network is how we know the energy figure with reasonable confidence. Optical observations gave the brightness, and infrasound gave the yield independently. This network has quietly become one of the more useful tools in this field. It detects airbursts over open ocean that nobody sees or reports. It has recorded dozens of events in the kiloton range over the past 2 decades. Most of them happened over water or wilderness and were noticed by nobody. So we have a reasonably complete record of what has arrived recently. We simply have no comparable record of what is still out there. That was the largest object known to strike our atmosphere since 1908. Hold that year, because I need it very shortly, and it involves a considerably larger rock. Part 5. Why a rock 3 times wider hits 30 times harder. There is a mental model most people carry about impacts, and it badly understates the risk. The reasoning goes roughly like this, and it sounds sensible enough. Bigger rock means bigger crater, scaling up in simple proportion. Double the size of the object and you get double the damage. That model is wrong, and correcting it matters more than almost anything here. The error involved is not small, and it runs in the dangerous direction. It is off by orders of magnitude at exactly the sizes that matter. The energy an impactor delivers equals 1/2 its mass times its velocity squared. That is the standard kinetic energy relationship, and it has 2 consequences that compound. Both of them work against us, and neither is intuitive. Start with velocity, because it is the simpler of the 2. Velocity appears squared in that equation, not as a plain multiplier. An object arriving at 20 kilometers per second carries far more energy. It does not carry twice the energy of one arriving at 10. It carries 4 times the energy of the slower object. That matters because approach speeds vary considerably across the near-Earth population. Some objects arrive at 11 kilometers per second, which is roughly the minimum possible. Others come in at 30 or more, particularly those on retrograde or steeply inclined orbits. That spread alone produces almost a 10-fold difference in delivered energy. Now take the second consequence, which is the one that genuinely reshapes the picture. Mass does not scale with width, And that is the crucial point. Mass scales with the cube of width, which changes everything downstream. Double the diameter of a rock, and you have not doubled its mass. You have multiplied it by 8, because volume grows in 3 dimensions. Triple the diameter, and you have multiplied the mass by 27. Quadruple it, and the mass is 64 times what you started with. Let me run that against real objects rather than leaving it abstract. Take the Chelyabinsk body again, at roughly 20 meters across. Now consider an object at 60 meters, exactly 3 times wider. That object is not 3 times more energetic on impact. Do not let that number slide past you without examining it. It is roughly 27 times more energetic before accounting for any speed difference. 27 times the energy from a rock that looks barely different through a telescope. Let me convert these sizes into energy figures so the ladder becomes concrete. A rock 10 meters across arriving at typical speed releases a few kilotons. That is comparable to a large conventional munition, detonated high in the atmosphere. At 20 meters, the Chelyabinsk scale, you reach 400 to 500 kilotons. Roughly 30 times the weapon used at Hiroshima in 1945. At 50 to 60 meters, the Tunguska scale, you reach 10 to 15 megatons. That is comparable to the largest weapons held in most national arsenals. At 140 meters, the congressional threshold, you approach 300 megatons. That exceeds the yield of any weapon ever detonated by any country. Each step up that ladder is only a modest change in apparent size. Through a telescope, a 20-meter rock and a 60-meter rock look nearly identical. The difference between them is the difference between broken windows and a flattened region. I want to apply this directly to the objects that passed us this week. It changes which one you should have been paying attention to. 2026 OX3 came in at around 14 meters across. Its speed was 9.45 kilometers per second relative to Earth. Both of those figures sit below the Chelyabinsk object in size and speed. Had it entered the atmosphere, it would have burst high and spectacularly. You would have a fireball, a sonic boom, and possibly some cracked windows nearby. Dangerous only if you happen to be standing in one specific unlucky place. Now take 2026 KU3, which passed on the 24th of July. Its estimated diameter runs between 60 and 135 meters. It passed at 7.68 lunar distances, which is a comfortable and unremarkable margin. At the low end of that size range, 60 meters, you are in Tunguska territory. At the high end, 135 meters, you approach the threshold written into United States law. That single object, generating no headlines whatsoever, carried hundreds to thousands of times the destructive potential. Compare that against the rock that passed closest and got the attention. That mismatch is the misdirection I want you to notice, and it repeats every single week. Public attention tracks proximity because proximity is the number that sounds dramatic. Physics tracks size and velocity, which produce no headline at all. Those two metrics almost never point at the same object. Think about watching a highway at night with a flashlight that reaches one lane. You would accurately report every car passing within a few meters of you. You would completely fail to notice the fuel tanker 3 lanes over. Your report would be precise, verifiable, and nearly useless for assessing actual danger. Keep that flashlight in mind, because I will return to it later. It describes not just news coverage, but the detection system itself. We report what we can see, and what we can see is not chosen by risk. Now let me build out the size ladder properly, because you need the full range. I am going to give you 4 tiers, and each behaves fundamentally differently. At 1 to 10 meters, objects enter the atmosphere regularly and produce fireballs. Something in this range hits us several times a year, and mostly nobody notices. They burst high, they scatter fragments, and occasionally a meteorite lands in a field. This is background noise rather than hazard, and it always has been. At 10 to 30 meters, you are in the Chelyabinsk band. These air burst high enough that the ground escapes direct destruction. But the pressure wave arrives with enough force to shatter glass across a city. Injuries in the hundreds or thousands are plausible, deaths are possible, and the event is survivable. These arrive on average every 50 to 100 years somewhere on Earth. At 50 to 140 meters, the character of the event changes completely. The object no longer disintegrates harmlessly high up in the atmosphere. It penetrates deeper before releasing its energy, where it reaches the ground intact. The energy release moves from hundreds of kilotons into the megaton range. A metropolitan area beneath one of these does not survive as a functioning city. These arrive on average every 500 to 1,000 years for the smaller end. Above 140 meters, you leave city-scale destruction and enter regional catastrophe. That is the threshold written into United States law 2 decades ago. These arrive on average every 20,000 years or so, and above 1 kilometer you reach the civilization-ending category, which I will handle separately. Those are rare, and the good news about them is genuinely good news. I want to make sure one thing about those intervals is clear, because people misread them constantly. An average interval of 500 years does not mean we are due or overdue. It does not mean we are safe for 5 centuries after the last one. These are random processes rather than scheduled appointments on a calendar. The correct reading of a 500-year average is a yearly probability. That probability is roughly 1 chance in 500 every single year. That probability does not decrease because an event happened recently, and it does not accumulate simply because none has happened lately. Each year is independent, and the dice have no memory of previous rolls. Now let me make that number tangible in a way that should unsettle you slightly. If your plane carried a 1 in 500 chance of crashing, you would not board. Sit with that comparison for a second before I continue. That is a risk level we consider completely unacceptable in every other context of life. A 1 in 500 annual chance of a city-scale airburst is roughly where we live. That has been true for the entire existence of this species. It was true in 1908, and it was true last Tuesday. Most of the time nothing happens to anyone, and the reason is simple geography. Roughly 70% of this planet is ocean, and much of the remainder is empty. A Tunguska-class object has an overwhelming probability of landing where nobody lives. Chelyabinsk was unusual precisely because a rock that size arrived over a city. There is one more variable that changes these outcomes dramatically, and it is entry angle. 2 identical rocks arriving at identical speeds can produce very different events. An object entering steeply, close to vertical, spends little time in dense air. It penetrates deeper before disintegrating, and it releases its energy lower down. Lower detonation means a more concentrated pressure wave on the ground beneath. It also means a higher chance of fragments surviving to the surface. An object entering at a shallow angle travels a long path through the atmosphere. It encounters far more air, decelerates more gradually, and bursts higher up. The energy spreads across a wider area, and the peak pressure at ground level falls. Chelyabinsk arrived at a shallow angle of roughly 20 degrees from horizontal. That geometry is one of the main reasons nobody died that morning. A steeper entry over the same city would have produced a very different list. So the outcome of an impact depends on size, on speed, and on angle. 3 variables, none of which we can influence, and only one we can estimate in advance. Now let me address the scenario that covers most of this planet's surface. Roughly 70% of Earth is ocean, so most impacts land in water. There is a persistent belief that this is straightforwardly good news. for small objects that belief is genuinely correct, without any qualification. A 20-meter rock bursting over open ocean is a complete non-event. This happens periodically and nobody notices except for infrasound sensors. For larger objects, the picture is contested, and I will not pretend otherwise. Two views exist in the scientific literature, and they disagree meaningfully. The optimistic view notes that impact waves differ from earthquake tsunamis. An earthquake displaces a fault line hundreds of kilometers long. That produces waves with enormous wavelengths that carry energy across entire ocean basins. An impact produces a localized cavity, and those waves disperse far more rapidly. The pessimistic view emphasizes what happens at the coastline itself. Coastal geometry can amplify waves enormously as they enter shallow bays. A substantial share of humanity lives within a few kilometers of a shore. Both camps agree on the part that matters for this story. The danger is not the wave in mid-ocean, but the wave arriving at a specific coast. Predicting which coast requires an orbit determined years ahead of the event, which is once again the same bottleneck under a different disguise. That is the coin landing on its edge, in front of witnesses. It happened within the lifetime of most people watching this. Hold that thought, because I now need to show you what the larger tier does. There is a morning in Siberia that answers the question exactly. Part 6. 80 million trees, and nobody there to count them. On the 30th of June, 1908, an explosion occurred over Siberia. The time was around 7 in the morning, local time. It happened in the air above the Podkamennaya-Tunguska River in central Siberia. The nearest substantial settlement sat tens of kilometers away from the blast. That distance is the only reason this story lacks a body count. Current estimates place the object at somewhere between 50 and 60 meters in diameter. The energy released is estimated at between 10 and 15 megatons of TNT equivalent. Set that against Chelyabinsk, which released 440 to 530 kilotons. A rock roughly 3 times wider produced an explosion roughly 30 times more energetic. That is the cubic scaling I described, appearing directly in the historical record. The blast flattened more than 2,000 square kilometers of forest. Estimates put the number of trees knocked down at around 80 million. 80 million trees laid flat in a pattern that told investigators exactly what happened. Directly beneath the airburst, the trees remained standing but were stripped completely bare. Their branches were gone, but the trunks stayed upright, which puzzled early investigators enormously. The explanation is that the pressure wave arrived from directly overhead there. With no lateral component, there was nothing to push the trunk sideways. Radiating outward from that central zone, the picture changes completely. For tens of kilometers in every direction, the trees lie flat and point away. They fell in a radial pattern, like iron filings arranged around a magnet. That pattern is how investigators located the exact point of the explosion decades later. Nobody was killed, as far as any surviving record indicates. That outcome is entirely and purely a matter of geography and nothing else. It happened over one of the emptiest inhabited landmasses on this planet. The accounts from those who were present are worth hearing. Trading Post records from the region describe people being knocked off their feet. Some of those accounts came from distances of 60 kilometers and more from the center. One witness described the sky splitting open and the air becoming too hot to bear. The event registered far beyond Siberia in instruments that had no idea what they recorded. Seismic stations across Europe picked up the resulting ground motion clearly. Atmospheric pressure sensors in Britain recorded the wave passing overhead. Unusual bright nights were reported across Europe and Asia for days afterward. Now let me do the thing that makes this number mean something to you. 2,000 square kilometers of total destruction is an abstraction until you map it. The land area of Greater London is roughly 1,570 square kilometres. The 5 boroughs of New York City total about 780 square kilometres. The entire territory of Singapore covers around 730 square kilometres. The city of Tokyo proper spans roughly 627 square kilometres. An event of the Tunguska class centred on any of those does not damage the city. Read that last figure again before you move past it. It removes the city entirely, along with a substantial ring of everything surrounding it. That is what a 50 to 60 metre object does when it arrives over land. And 50 to 60 metres sits inside the size range of 2026 Ku3. That object passed this planet 6 days ago, at a comfortable distance, generating no coverage. Before I move on, let me make the human scale explicit for a modern event. Tunguska produced no casualties because it arrived over empty forest. Consider the same object arriving over a metropolitan area of 10 million people. The pressure wave that flattened 80 million trees does not distinguish between trees and buildings. Structures within the radial zone would suffer catastrophic structural failure. Beyond that, the glass breakage radius extends considerably further still. Studies of airburst effects generally place severe blast damage across hundreds of square kilometres. The thermal pulse would ignite fires across a similar area simultaneously. Emergency services would be operating inside the damaged zone rather than outside it. Nobody can give you a reliable casualty figure for that scenario. The estimates in the literature span an enormous range, depending entirely on assumptions. Population density, building construction, time of day, and burst altitude all dominate the result. What is not in dispute is the order of magnitude of the affected area. A 50-metre object arriving over a city produces a national catastrophe, not a disaster requiring assistance, but an event that reshapes a country's history. That is the scenario the entire detection effort exists to prevent. And it is the scenario that falls outside the legal mandate entirely. I want to be scrupulous here, because I can feel the shape this argument wants to take. 2026 Ku3 was never a threat to anyone at any point. It passed at nearly 3 million kilometres, which is not remotely a near miss. Presenting a routine flyby as a close call is dishonest, and I will not do it. The point is not that this particular rock nearly hit us. Weigh what I am claiming here against what I am not. The point is that objects in the Tunguska class move through this neighbourhood routinely. We now detect a fraction of them, often days or hours before closest approach. 20 years ago we would have detected none of them at all. It took 19 years before anyone reached the site of that explosion. The first scientific expedition was led by Leonid Kulik, arriving in 1927. Kulik expected to find a crater, because that is what impacts were assumed to produce. He searched extensively across the flattened forest and found nothing of the kind. There was no crater, no central pit, and no substantial fragment of the object. That absence baffled investigators for decades and fed a great many strange theories. The resolution is the physics I described earlier, which was not understood at the time. The object never reached the ground at any point in its descent. It disintegrated in the air and delivered its energy as a pressure wave. Kulik's photographs of the standing dead trees beneath the burst point remain striking. Bare trunks, stripped of branches, standing upright in the middle of total devastation, radiating outward from them, 80 million trees lying flat in a perfect pattern. Now let me place Tunguska against the largest impact in the geological record. The Chelyabinsk impactor struck the Yucatan Peninsula around 66 million years ago. Estimates put it between 10 and 15 kilometres in diameter. Run the cubic scaling on that comparison and the gap becomes clear. Tunguska involved an object of around 55 metres in diameter. Chicxulub was roughly 10,000 meters, nearly 200 times wider. That means a mass ratio in the region of 6 million to 1. The energy released at Chicxulub is estimated in the range of 100 million megatons. Tunguska released perhaps 15 megatons, by the best current estimates. The event that ended 3/4 of species on this planet was not a bigger Tunguska. It belonged to a completely different physical regime altogether, not merely a larger scale. I want that comparison on the record for a specific reason. The extinction class impact is the one everyone pictures, and it is effectively solved. We have found over 90% of the objects in that class. None of them is on a path that brings it here. The events that will actually happen to human beings sit thousands of times smaller. They do not end civilization, and they never appear in films about asteroids. They flatten a region, or they break every window in a city, and the entire detection effort is calibrated toward the tier we already handled. Stay with me here, because the next part of this is where the record gets uncomfortable. Tunguska happened in 1908, before anyone was systematically searching the sky. The obvious assumption is that a modern survey network would catch such an object early. That assumption has already been tested in living memory, and the result was not reassuring. Part 7. The city killer we found with 24 hours left. On the 25th of July, 2019, an asteroid designated 2019 OK passed Earth. Its closest approach brought it within approximately 73,000 kilometers of this planet. Let me establish what that distance actually means before going further. 73,000 kilometers is 0.19 lunar distances. It is roughly a fifth of the way to the Moon from here. The ring of geostationary communication satellites orbits at about 35,800 kilometers. So this object passed at roughly twice the altitude of those satellites. Those satellites carry television, weather monitoring, and a substantial share of global communications. The rock passed through the outer neighbourhood of infrastructure that modern life depends on. Estimates of its size range from about 57 metres to 130 metres. Even at the bottom of that range, this was a Tunguska-class object. At the top of that range, it approached the 140-metre threshold. We discovered it approximately 24 hours before it passed this planet. 24 hours of notice for an object capable of removing a metropolitan area. It moved through a region where small timing differences separate very different outcomes. I want to give you the reactions from the people who work in this field. Not because reactions are evidence, but because they tell you how insiders read the event. Alan Duffy, an astronomer at the Royal Institution of Australia, described it in stark terms. He said it would have gone off like a very large nuclear weapon. He called it a clear and present danger, which is not typical scientific language. Michael Brown, an astronomer at Monash University, put it more plainly still. He said the object snuck up on us, and he did not soften it. And then there is the internal reaction, which became public through released emails. Lindley Johnson was NASA's Planetary Defense Officer at the time, and he coined that job title. In his own correspondence, he wrote that this one did sneak up on us. Sit with that admission for a moment before we move on. The senior official responsible for planetary defense at the largest space agency, describing an object in the City Killer class as having snuck up on his network. So why did 2019 OK evade detection until the final day? Several factors stack together, and each one is worth understanding separately. Its approach geometry placed it against a crowded and complicated region of sky. It was faint during the critical weeks when early detection would have been possible, and its apparent motion across the sky was unusually slow for much of that period. The last factor is the one I flagged earlier, and here it is in the historical record. Track this next piece closely, because it explains the whole failure. Discovery software finds asteroids by detecting position change between exposures. an object approaching nearly head-on produces very little apparent motion. Such an object hides inside the fundamental weakness of the detection method. Now I want to balance this, because a story built only on failures misleads you. The same network that missed 2019 OK has succeeded spectacularly several times. On the 6th of October 2008, the Catalina Sky Survey detected a small object. It was designated 2008 TC3, and analysis of its orbit produced something unprecedented. The object was going to hit us, and we knew where and we knew when. 19 hours later, it entered the atmosphere over northern Sudan and exploded at altitude. It arrived exactly where predicted and exactly when predicted, to within minutes. Fragments were later recovered from the Nubian desert by search teams on foot. That recovery mattered enormously, for reasons reaching well beyond planetary defense. For the first time, a meteorite in a laboratory could be matched to telescope observations. Scientists could connect what a rock looked like in space with what it contained. It has happened repeatedly since then, which tells you the capability is real. In 2014, another small object was caught before atmospheric entry. In June of 2018, an object designated 2018 LA was detected. That detection came roughly 8 hours before it burst over Botswana, and fragments were recovered. In December of 2024, another object was spotted hours before entering over Siberia. So the warning pipeline functions, and it functions quickly when conditions cooperate. From first detection to a predicted impact location and time in hours, every one of those objects was tiny, and that is not a coincidence. 4 meters, 3 meters, small enough that the impact was a light show. Objects that small only become detectable when they are already extremely close. And when they are extremely close, their remaining trajectory is simple to project. There is an institutional layer above the telescopes that almost nobody knows exists. It deserves naming, because it is the machinery that would actually respond. The International Asteroid Warning Network, known as IORN, is responsible for issuing warnings. It coordinates observations across national boundaries and verifies findings before they go public. It communicates assessments to governments, which is a harder job than it sounds. Kelly Fast, who I will discuss further later, serves as its coordinating officer. Alongside it sits the Space Mission Planning Advisory Group, known as SMPAG. Commit these 2 acronyms to memory, because they matter later. That body would plan an actual mitigation mission if one became necessary. It convenes the space agencies capable of building and flying something on short notice. Its purpose is to have deflection options analysed before anyone urgently needs them. There is also a rehearsal culture in this field that deserves mention. Every 2 years, the international community runs a planetary defence exercise. Participants are given a fictional asteroid with a fictional impact probability. They then work the problem in real time over several days. Those exercises have repeatedly produced the same uncomfortable conclusion every time. The technical response is usually adequate, given sufficient warning time. The decision-making process is where these scenarios reliably break down. Who decides to attempt a deflection, and which nation actually launches it? What happens if a deflection shifts the impact point from one country to another? Those questions have no established answers, and the exercises keep surfacing them. One recent exercise scenario involved an object with a decade of warning. Participants concluded that international agreement on a response would consume years. The technical mission would then need to be built inside the remainder. I raise this because the detection gap is only the first problem. Finding the object is necessary, and it is nowhere near sufficient. Everything after detection runs through institutions that have never faced this decision. Both bodies were exercised for real in the last 2 years, against a genuine candidate. That episode is the centerpiece of this story, and I will get there shortly. There is one more object that belongs in this part, and it has a date attached. It is the most famous asteroid in the world, and it is coming back. Apophis was discovered in 2004, and it caused genuine alarm immediately. Early orbit solutions gave it a meaningful probability of striking Earth in 2029. It reached level 4 on the Torino scale, the highest ever assigned. That remains the record, and no object has matched it since. Further observations then did what further observations reliably always do. The uncertainty region shrank, the searchlight narrowed, and Earth fell outside the beam. An impact in 2029 was ruled out, and later dates were cleared as well. But the flyby itself still happens, and the numbers are extraordinary. On the 13th of April 2029, Apophis passes within about 31,000 kilometers. Some solutions put it closer to 38,000, and the figure continues to refine. Compare that against the geostationary satellite ring at 35,800 kilometers. Apophis will pass through the altitude band where our communication satellites operate. David Farnokia of the Center for Near-Earth Object Studies has stated it directly. He has noted it will come closer than our geostationary satellites. The object is roughly 340 meters across, well above the congressional threshold. It will be visible to the naked eye from parts of Europe and Africa. Roughly 2 billion people will be able to watch it pass without a telescope. That event is under 3 years away, and it is entirely safe. It is also the single best opportunity this century to study such an object. Earth's gravity will physically deform Apophis as it passes, reshaping its surface. Several agencies are planning missions to observe that deformation as it happens. Hold that date, because it is the one moment when this subject gets public attention. 2 billion people looking up at a rock that was once rated a genuine threat. Whether that attention translates into anything durable is a separate question entirely. For now, hold the contrast that this part has built. We can predict a 4-meter rock's impact point 19 hours out. We can miss a 100-meter rock until 24 hours before it passes. The difference between those two outcomes has almost nothing to do with size. It has everything to do with the direction the object approaches from, and that brings us to the law that was supposed to close this gap. Part 8. The deadline that came, went, and nobody noticed. In December of 2005, the United States Congress passed a specific piece of legislation. It was named the Near-Earth Object Survey Act, after Congressman George Brown. It was signed into law on the 30th of December of that year. The instruction it gave NASA was unusually concrete for legislation about science. Detect, track, catalogue, and characterize near-Earth objects of 140 meters or larger. Achieve 90% completion of that catalogue within 15 years of enactment. 15 years from 2005 brings you to 2020. That deadline arrived and passed more than 5 years ago. Here is where that catalogue actually stands as of today. Depending on which population estimate you use, NASA has found roughly 45%. That represents somewhere around 11,200 objects of that size found. NASA's own published figure several years ago was approximately 40%. Call it somewhere between 40 and 45% as of this month. The legal requirement was 90% completion by the year 2020. The achieved figure is under half, in mid-2026. I want to be careful about how that gets framed, because the easy framing is wrong. This is not a story about negligence or incompetence by astronomers. The people running this program have found more objects per dollar than almost anyone. They built the network I described earlier on budgets that would embarrass a mid-sized company. The mandate was missed because Congress passed a requirement without funding the instrument to meet it. You cannot reach 90% completeness from the ground, for reasons I have already explained. The blind spot is physical, and no ground-based effort at any budget closes it. That is a structural fact about how the requirement was written, not a failure of effort. But the consequence is identical regardless of where blame sits. Right now, tonight, more than half of the objects that could devastate a region remain uncatalogued. They are not undiscovered in the sense of not existing at all. Their orbits are already determined by physics and have been for millions of years. No human being has ever recorded a single one of them. Now notice what the 140-meter threshold excludes, because this is the crucial part. It excludes everything smaller, which is the overwhelming majority of dangerous objects. Look at the actual historical record of what has struck this planet in modern times. Chelyabinsk was 17 to 20 meters, far below the threshold. Tunguska was 50 to 60 meters, still well below the threshold. 2019 OK was 57 to 130 meters, below it at the low end. Essentially every significant modern event involves an object the mandate does not cover. The law was written to catch the objects that could end a region. It was never written to catch the objects that could end a city. And city killers are vastly more numerous and considerably harder to detect. Let me say that differently, because it is the central irony of this entire field. The rocks we are legally required to find are not the rocks that keep hitting us. Let me lay out the full risk picture as a set of layers. Presenting it as a single undifferentiated threat is what causes both panic and dismissal. The top layer is the extinction class object at 1 kilometer and larger. The Chicxulub impactor struck the Yucatan Peninsula around 66 million years ago. It measured somewhere between 10 and 15 kilometers in diameter. This is the layer that dominates public imagination and film. It is also, at this point, the layer we have largely handled. Over 90% of near-Earth objects above 1 kilometer have been found and catalogued. None of them threatens Earth in any time frame that concerns anyone currently alive. That threat is, as far as our knowledge extends, retired. That is a genuine achievement, and it deserves to be stated clearly. The second layer is the regional destroyer at 140 meters and above. Impact intervals of roughly 20,000 years, and the legal mandate covers this layer. We are somewhere under half complete on it, 21 years after the law passed. The third layer is the city killer, between 50 and 140 meters. Intervals of roughly 500 to 1,000 years for the smaller members. This layer has no legal mandate covering it at all, anywhere. It is also the most numerous of the genuinely dangerous categories. The fourth layer is the window breaker, between 10 and 30 meters. Chelyabinsk sits here, and so does the rock that passed us on Monday. Intervals of 50 to 100 years, which means most people alive will see one. Now look at where our capability sits relative to our actual exposure. Line those 4 layers up in your mind for a moment. We have comprehensively solved the layer that occurs every 100 million years. We are half done on the layer that occurs every 20,000 years. We have no mandate on the layer that occurs every several hundred years. And we have no realistic prospect of ever cataloguing the most frequent layer. Our coverage is almost perfectly inverse to the frequency of the event. That is not irrational, and I want to defend the people who made those choices. Weighted purely by expected total casualties, the priority order is correct. One extinction event outweighs an enormous number of Chelyabinsk's in raw arithmetic. But expected value reasoning carries its own blind spot, and it is a serious one. It tells you where to spend the next dollar with real precision. It tells you almost nothing about the specific Tuesday when a rock arrives. I should explain where the population estimates themselves come from, because the method matters. When I say we have found 45%, that implies knowing the total. And the total is by definition made of objects we have not found. The technique relies on rediscovery statistics, and the logic is elegant. Surveys repeatedly detect objects they have already catalogued alongside genuinely new ones. Track the ratio of known to new detections over time, and it tells you something. If almost everything you detect is already known, your catalogue is nearly complete. If most detections are new objects, you are still early in the search. Apply that reasoning with proper statistical machinery, and you get a population estimate. The current figures come from Bayesian analysis of exactly this kind of data. That is why the answer is expressed as approximately 45% rather than precisely. Roughly 11,200 objects above 140 meters are catalogued. The estimated total population is therefore somewhere around 25,000 objects, which leaves something on the order of 14,000 unaccounted for. 14,000 objects, each capable of devastating a region with orbits nobody has calculated. I want to place one more set of facts beside that figure without editorializing. The office responsible for coordinating this work is the Planetary Defense Coordination Office. Lindley Johnson, its first planetary defense officer, retired on the 15th of May 2025. He had served 22 years of federal service and created the role itself. Kelly Fast has served as acting planetary defense officer since that departure. She simultaneously serves as Near-Earth Object Observations Program Manager. She also serves as coordinating officer for the International Asteroid Warning Network. 3 substantial roles held by one person in an acting capacity. As of last year, the office was operating with minimal permanent staff. That meant roughly 1 full-time civil servant and 1 contractor. Those are the people standing between an incomplete catalogue and the 14,000. Hold that tension, because everything that follows lives inside it. And the first thing that follows is the one occasion when we fought back. Part 9. The night we deliberately moved another world. On the 26th of September 2022, at 23:14 Universal Time, something remarkable happened. A spacecraft roughly the size of a vending machine struck an asteroid moonlet. It hit at 6.1 kilometers per second, and it was destroyed instantly. The mission was called DART, which stands for Double Asteroid Redirection Test. Its target was Dimorphos, a small moon about 160 meters across. Dimorphos orbits a larger asteroid called Didymos, which measures roughly 780 meters. Neither object ever posed any threat to Earth, and that was deliberate. You do not test a deflection technique on something aimed at your own planet. The pair was chosen for safety and for one enormously convenient property. That property was the moonlet's orbit, which functioned as a clock we could read. Let me explain why that mattered so much to the mission design. Measuring whether you have changed an asteroid's orbit around the Sun is extraordinarily hard. The changes are tiny, the orbit is vast, and confirmation takes years of tracking. But measuring a moonlet's orbit around its parent asteroid is comparatively straightforward. Every time Dimorphos passed in front of Didymos, telescopes on Earth saw a dip. The combined brightness of the pair fell slightly, then recovered. Time those dips before the impact, then time them afterward. The difference between those 2 measurements tells you precisely what you accomplished. Before impact, Dimorphos completed 1 orbit of its parent in 11 hours and 55 minutes. That figure was known with high confidence from years of ground-based observation. 2 weeks after the impact, NASA announced the orbital period had shortened by 32 minutes. The stated uncertainty on that figure was plus or minus 2 minutes. A more careful analysis followed, led by researchers at the Jet Propulsion Laboratory. It refined the figure to a reduction of 33 minutes and 15 seconds. The new period stands at 11 hours, 22 minutes and 3 seconds. The accuracy of that measurement is roughly 1.5 seconds. Now here is the number that makes this mission extraordinary rather than merely successful. The pre-mission success criterion was a period change of 73 seconds. Anything above that figure would count as a demonstrated deflection. We achieved 33 minutes, which nobody involved had seriously expected. That is roughly 27 times the threshold that defines success. Fix that number in your memory, because it is the good news. Why did it work so much better than the conservative estimate predicted? This is the genuinely interesting physics, and it deserves a proper explanation. Imagine throwing a tennis ball hard at a brick wall. The ball bounces back, and the wall absorbs some momentum from the collision. The total push on the wall is roughly the ball's momentum, perhaps a little more. Now imagine throwing that same tennis ball into a pile of dry sand. The ball buries itself, and a spray of sand erupts backward out of the crater. That spray carries momentum in the opposite direction to your throw. By conservation of momentum, every grain thrown backward pushes the pile forward. Dart did not hit a brick wall out there at Dimorphos. It hit something far closer to the pile of dry sand. The impact blew an enormous plume of material off the surface of Dimorphos. That ejector carried away far more momentum than the spacecraft itself delivered. Scientists quantify this with a factor called beta, which measures the amplification. If the spacecraft simply buried itself with no ejector, beta would equal 1. Under that scenario, the period change would have been around 7 minutes. The measured beta came out somewhere between 2.2 and 4.9. Remember that sand pile, because it returns later when I discuss what asteroids are made of. The looseness of the target was the difference between 7 minutes and 33. DART produced a second result that received almost no public attention. It measurably altered the orbit of the entire Didymos system around the Sun. Not just the moonlet around its parent, but the pair around our star. That is the first time in the entire history of this species. We changed the solar orbit of another celestial body on purpose, deliberately, by design, with a calculated result that matched prediction. I think that deserves a moment of genuine appreciation before I complicate it. And now I have to complicate it, because the mission's conditions were not realistic. Every single advantage DART enjoyed is an advantage we would not have in an emergency. DART launched in November of 2021 and impacted in September of 2022. The mission was conceived, funded, designed and built over roughly a decade before that. Its target was an object whose orbit had been characterized precisely for years. Dimorphos sat exactly where predicted, arriving exactly when predicted, with no surprises. Now compare that against an object discovered 36 hours before closest approach, or an object like 2019 OK, found 24 hours out, or Chelyabinsk, which was found by the people it injured. The technique we validated requires two conditions that we frequently do not have. It requires knowing that the object exists in the first place, and it requires knowing early enough to design, build and fly a spacecraft. I want to be precise about what early enough actually means, because it surprises people. A kinetic impactor does not shove an asteroid sideways out of Earth's path. Here is where most people's intuition about deflection breaks down entirely. It cannot, and the mass ratio makes that obvious when you examine it. The DART spacecraft weighed roughly 600 kilograms at the moment of impact. Dimorphos weighs somewhere in the region of 5 billion kilograms. The ratio is comparable to a mosquito striking a freight truck. What the impactor actually does is change the object's speed along its existing orbit, by a tiny amount measured in fractions of a millimeter per second. And then you wait, and the waiting is the entire technique. Over years and multiple orbits, that tiny speed change accumulates into a large positional difference. The asteroid arrives at the crossing point minutes or hours earlier or later. Earth has moved along its own orbit in that time. The two objects miss each other, and the miss can be enormous. You are not deflecting the rock in any intuitive sense. You are deflecting the rock's schedule, and schedules take years to slip meaningfully. Kinetic impact is not the only technique on the table, and the alternatives are instructive. Each one trades speed for precision in a different way. The gravity tractor is the most elegant and the slowest. A spacecraft flies alongside the asteroid and simply stays there. Its own mass exerts a tiny gravitational pull on the object. Over years, that pull draws the asteroid gently onto a new path. The advantage is precision, because you can adjust continuously and measure the result. The disadvantage is time, because the force involved is minuscule. The gravity tractor requires decades of warning to be useful at all. The ion beam shepherd works on a similar principle with an active push. A spacecraft directs an ion thruster at the asteroid's surface from close range. The momentum of that beam pushes the object slowly and controllably. Then there is the nuclear option, which sits at the opposite end. The technique is not to destroy the object, which is a common misconception. It is to detonate a device at a standoff distance beside it. The radiation flash vaporizes a thin layer of the surface. That vaporized material blows off, pushing the asteroid the other way. That approach delivers far more momentum change than any other method. It is also the only option with a realistic chance on short notice. It has never been tested, and several treaties complicate testing it, and the failure mode, fragmentation into multiple lethal pieces, remains genuinely possible. So how much warning does each response option actually require? Let me lay that out clearly, because it is the practical core of planetary defense. With 10 to 20 years of warning, kinetic deflection is plausible for a city killer. You have time to build the spacecraft, fly it, verify the result, and try again. That last point matters more than people realize, because one attempt may not suffice. With roughly 1 year of warning, you are in serious difficulty. Building and launching an interceptor on that timeline has never been attempted. You would likely be discussing a nuclear standoff detonation, which has never been tested. That technique carries its own catastrophic failure modes, including fragmenting the object. Multiple lethal pieces on the same trajectory is not an improvement over one. With 1 week of warning, there is exactly one available response. Evacuate the predicted impact zone and the coastline if the impact is oceanic. With 24 hours, which is what 2019 OK gave us, evacuation is impossible. You cannot move a metropolitan population anywhere in a single day. What you can do is tell people to stay away from windows. Hold that, because it turns out to be the most important sentence in this entire story. I will come back to it near the end, and it will look different then. DART did not fly alone, and its companion produced the images everyone remembers. A small Italian satellite called Lysacube rode along and separated 15 days before impact. It trailed the main spacecraft by a few minutes, which was the entire point. DART could not photograph its own impact for obvious reasons. Lysacube flew past Dimorphos shortly afterward and photographed the aftermath directly. What it captured was not a neat crater with a plume above it. It recorded an enormous structured cloud of debris streaming away from the surface. Filaments and streamers extended for hundreds of kilometers within minutes. Ground telescopes and the Hubble Space Telescope tracked that debris for weeks afterward. A tail formed behind Dimorphos, and the object briefly resembled a comet. At one point the tail extended more than 10,000 kilometers. That is what a beta between 2.2 and 4.9 looks like from outside. An enormous quantity of material leaving the asteroid faster than the spacecraft arrived. There is a second finding that emerged from analysing DART's final images. In the last seconds before impact, the camera resolved the surface in detail. Dimorphos is covered in boulders, some of them several meters across. The spacecraft struck between two of them rather than on smooth terrain. Subsequent modelling suggests the impact did more than excavate a crater. It may have substantially reshaped the entire moonlet, deforming it globally. A body held together weakly can be reformed by an impact, rather than cratered. That distinction matters enormously for anyone planning a real deflection. If your impactor reshapes the target instead of pushing it cleanly, prediction becomes far harder. It also raises a question nobody can currently answer confidently. Could a kinetic impact fragment a threatening object rather than deflect it? A rubble pile struck hard enough might separate into multiple pieces. Several smaller objects on nearly the same trajectory is not obviously an improvement. That failure mode has been discussed in the literature for 2 decades. It has never been tested, and DART was deliberately designed to avoid it. The impact energy was kept modest relative to the target's mass. Hold that concern because it is one of the specific questions Hero exists to settle. For now, there is a spacecraft in flight right now that is about to change these calculations. It arrives in about 3 months, and almost nobody is talking about it. Part 10. The spacecraft arriving in November to grade our homework. The European Space Agency launched a mission called Hera on the 7th of October 2024. It flew on a Falcon 9, and its destination is Didymos and Dimorphos. It is going to the exact same pair of rocks that DART struck. Its job is forensic, and the question it answers is more important than it sounds. Here is the specific problem that Hero was built to solve. DART changed the orbital period of Dimorphos by 33 minutes and 15 seconds. That is a beautifully precise measurement, and it is not enough. To convert that measurement into engineering knowledge, you need the mass of the target. Momentum is mass multiplied by velocity, and that relationship is not negotiable. If you know the velocity change but not the mass, you do not know the force. You know what happened without knowing why it happened to that degree. DART did not measure Dimorphos's mass for an unavoidable reason. Its final act was to stop existing at 6.1 kilometers per second. You cannot take careful measurements while you are disintegrating on impact. So beta, the ejector amplification factor, currently sits between 2.2 and 4.9. That is more than a factor of 2 in uncertainty on the key parameter. If you are planning a real deflection against a real incoming object, that range matters. It is the difference between a comfortable miss and a direct hit on a city. Hero will measure the mass of Dimorphos directly, using an elegant technique. It will fly close enough that the moonlet's gravity perturbs its own trajectory, track those perturbations precisely from Earth, and the mass falls out of the mathematics. It will also photograph the crater DART excavated, which nobody has ever seen. The impact was observed from a distance, and the aftermath plume obscured the surface. We know we hit it, and we know roughly what happened afterward. We do not know what the impact site looks like. Hero will characterize the internal structure of a rubble pile asteroid for the first time. It carries 2 small satellites called Juventus and Milani that separate on arrival. Juventus carries a radar instrument designed to sound the interior of Dimorphos. That measurement has never been made on any asteroid, anywhere. The mission's cruise has gone well, which is not something you can assume. Hera performed a flyby of Mars and its moon Deimos on the 12th of March, 2025. That flyby bent its path using the planet's gravity, saving substantial fuel. In February and March of this year, it executed its largest deep space maneuver. The burn consumed 123 kilograms of hydrazine propellant. It changed the spacecraft's velocity by 367 meters per second. That maneuver performed well enough that Hera is now running ahead of schedule. It arrives at Didymos in November of this year, roughly a month earlier than planned. It will then study the system for around 6 months from close range. Its observation altitude will descend from 30 kilometers down to under 2 kilometers. So in about 90 days, the largest uncertainty in our only demonstrated defense begins resolving. That is a genuinely significant date, and it will receive a fraction of the attention it deserves. I want you to hold two clocks in your mind for the remainder of this story. They are running simultaneously, they are not synchronized, and the gap between them matters. The first clock is the discovery clock, and it never stops. It advances every time a survey telescope records an object nobody knew existed. It is currently accelerating because of Vera Rubin and improving detector technology. That clock is running faster now than at any point in history. The second clock is the capability clock, which moves in discrete steps. It advances when Hera arrives in November and returns its measurements. It advances when a particular telescope launches, which I will address later. It advances or stalls with each budget cycle in Washington and Paris. The entire question of whether this civilization is prepared reduces to those two clocks, not to whether an asteroid is coming, because the answer to that is always yes eventually. The question is, which clock is running faster when one arrives? Let me say more about the two CubeSats, because their instrument choices are revealing. Juventus is roughly the size of a shoebox and carries a low-frequency radar. That radar is designed to penetrate the body of Dimorphos entirely. Follow the instrument choices here, because they reveal what nobody knows yet. Radar at low frequencies passes through rock rather than reflecting off the surface. It returns echoes from internal boundaries, voids and density changes. In effect, it produces a cross-section of the interior. Nobody has ever obtained that measurement for any asteroid. Anywhere, we have inferred internal structure from density estimates and from spin rates. We have never actually looked inside one of these objects. Juventus will also attempt to land on the surface at the end of its mission. Landing is generous language for what will happen at that gravity level. Surface gravity on Dimorphos is roughly 100,000th of Earth's. A person standing there could jump off into orbit without much effort. Milani, the second small satellite, carries a multispectral imager instead. It will map the composition of the surface across both objects. Understanding what these bodies are made of feeds directly into deflection planning. Now let me return to the two clocks, because Hera advances one of them substantially. In November, the capability clock ticks forward by a meaningful amount. We move from having deflected something to understanding why the deflection worked. The discovery clock, meanwhile, has been accelerating for a different reason. Vera Rubin came online recently and is already producing thousands of new objects. Its 10-year survey will image the entire southern sky repeatedly. Here is why that repetition matters more than the raw discovery count. Rubin returns to the same fields on a planned cadence, night after night. That cadence is precisely what prevents an object from becoming lost. The follow-up problem I described earlier is partly solved by design, so both clocks are advancing right now, which is genuinely good news. The question is whether they advance faster than the catalogue gap closes. And there is one more variable that neither clock accounts for. It has been sitting in this story since the beginning, unmentioned. Now I need to introduce something that has been absent from this story so far. Everything I have described treats detection as a problem with a technological solution. Build better telescopes, place one in space, find the objects, calculate the orbits. That framing is correct as far as it goes, and it goes fairly far. But there is a second system involved that does not care about our schedules. Brace for a turn here, because the story changes direction. It sits about 150 million kilometers away, and it is entirely indifferent. 3 weeks ago it did something that should trouble anyone who relies on forecasting. Part 11. The one number nobody can forecast until it is already here. On the 30th of June this year, an active region on the Sun produced a flare. The region was designated 4479 and the flare was classified X1.1. Let me explain that classification, because the scale is not intuitive. Solar flares are graded by letter, and each letter represents a factor of 10. An M1 flare is 10 times stronger than a C1 flare. An X1 is 10 times stronger than an M1. X-class is the top of the scale, and it has no upper bound. That flare launched a coronal mass ejection, and I need to separate two things carefully. A flare and a coronal mass ejection are not the same phenomenon. They often occur together, but they behave completely differently and they arrive differently. A flare is light, in the most literal sense of that word. It is electromagnetic radiation, mostly X-ray and extreme ultraviolet emission. It travels at the speed of light, because that is what light does. It arrives here 8 minutes and 20 seconds after leaving the sun. There is no such thing as advance warning for a flare. The warning would have to travel at the same speed as the event itself. When a flare hits, its primary effect is on our upper atmosphere. It ionizes the daylit side, which degrades or blacks out high-frequency radio. A coronal mass ejection is matter rather than light, which changes everything. It is billions of tons of magnetized plasma physically thrown off the sun. It travels at typically 1 to 3 million kilometers per hour. That sounds enormous, and it is, but it is far slower than light. Crossing the distance to Earth takes a coronal mass ejection 1 to 3 days. That transit time is the entire foundation of space weather forecasting. It exists only because plasma moves slower than the light that announces it. So the coronal mass ejection from the 30th of June arrived on the 3rd of July. Forecasters at the Space Weather Prediction Center had assessed it in advance. Their assessment was that it would likely produce a G2 storm. G2 is moderate, producing aurora at high latitudes and mild power system effects. Early on the 4th of July, the storm intensified to G3. Strong, rather than moderate, which is 2 full categories higher. That put the event 2 full levels above the pre-arrival forecast. Aurora was reported as far south as New Mexico that night. People in the American Southwest photographed a sky that should not have been visible there. I want to be careful and honest about the significance of that, because inflation would be easy. A G3 storm is not a catastrophe by any measure. No power grid failed, no satellites were lost, nothing broke. In absolute terms, this was a moderate event that behaved somewhat worse than predicted. The significance of that night is not the severity of the storm. The significance is the size of the forecasting error involved. To understand why forecasters were wrong, you need one concept, and it governs everything. It is the single variable that determines whether a solar storm matters. Earth possesses a magnetic field, and that field is what protects us. It deflects the constant stream of charged particles flowing off the sun. A coronal mass ejection also carries a magnetic field, tangled up inside the plasma. The orientation of that internal field is essentially random from our perspective. It is determined by the magnetic structures on the sun that launched it. If the arriving cloud's field points northward, matching Earth's field at the contact point, they repel. The two fields push against each other, and the cloud slides around our magnetosphere. Very little energy transfers into our system, and you get a minor storm or nothing. If the arriving cloud's field points southward, opposing ours, something entirely different happens. The two fields undergo a process that physicists call magnetic reconnection. They splice together, and the magnetosphere effectively opens like a door. Enormous quantities of energy pour into the upper atmosphere, and the currents flowing through it. Same cloud, same speed, same density, and the same arrival time. The outcome, though, is radically different from one case to the other. The entire difference is determined by which way an invisible magnetic arrow points. Think of it like two magnets brought together in the dark. Turned one way, they snap together with real force between them. Turned the other way, they shove each other firmly apart. You cannot tell which orientation you have until they are almost touching. And that is precisely our situation with every incoming solar storm. We cannot measure the orientation of an arriving cloud remotely. We have to wait until it physically reaches a spacecraft that can sample it directly. That spacecraft sits at a location called the first Lagrange point. It is about 1.5 million kilometers sunward of Earth. From there, the plasma takes roughly 30 to 60 minutes to reach Earth. So the honest warning time for storm severity is not 1 to 3 days. Days of notice tell you that something is coming toward us. The warning about whether it matters is between 30 and 60 minutes. Let me put that another way, because it is the crux of this part. We get days of warning about the arrival and under an hour about the consequence. That is exactly what happened on the 4th of July. Forecasters made a reasonable estimate from the data available to them. The magnetic orientation turned out less favourable than the models assumed. The storm ran 2 categories hotter than predicted, and everyone found out on arrival. Now, where does the sun stand tonight on the 30th of July? I am going to give you the actual current state rather than manufactured drama. The sun is quiet tonight by the standards of this phase. That quiet is real, and it would surprise most people watching. Over the past 24 hours, the sun produced only C-class flares. The strongest was a C 1.9 from active region 4498. The Planetary K-index, which measures geomagnetic disturbance from 0 to 9, sits between 1 and 3. That range is classified as quiet to unsettled, which is entirely ordinary. One thing is in motion, and it deserves a mention for completeness. Active region 4494 carries a beta-delta magnetic configuration. That configuration is the one that tends to precede significant flares. On the 26th of July, it produced an M3.2 flare. The peak came at 15:29 Universal Time that afternoon. That flare launched a coronal mass ejection, and modelling puts its arrival late tonight. There is a possibility of a G1- storm on the 31st. A filament eruption on the 27th may deliver a glancing blow around the 1st of August. G1 sits at the very bottom of the storm scale. This is not an emergency, and I am not going to pretend otherwise. I want to give you 2 historical events that define the ceiling of this phenomenon. Both involved geomagnetic storms, and both have hard numbers attached. The first happened on the 13th of March, 1989, in Quebec. A severe geomagnetic storm induced currents in the province's long transmission lines. Those induced currents destabilized the grid's protective equipment within seconds. The first equipment tripped at 2:44 and 17 seconds in the morning. The entire Hydro-Quebec grid collapsed at 2:45 and 49 seconds. That is a total collapse in 92 seconds from the first fault. Roughly 21,350 megawatts of supply dropped off the network. Approximately 6 million people lost power, and it took about 9 hours to restore. The storm recorded the largest disturbance index of the 20th century. David Bottler of Natural Resources Canada has studied that event extensively. He calls it the biggest geomagnetic storm of the space age. Now go back further, to the largest event in the instrumental record. In September of 1859, an enormous solar eruption struck Earth directly. It is named the Carrington event, after the astronomer who observed the flare. Telegraph systems across Europe and North America failed during that storm. Operators reported sparks jumping from equipment and paper catching fire in some offices. Some telegraph lines continued operating after being disconnected from their batteries entirely. The induced currents alone were sufficient to carry the signals. Aurora was reported near the equator, including in Cuba and Hawaii. In parts of the northern United States, the light was bright enough to read by at night. hold that last detail, because it is the one that connects to this story. Bright enough to read a newspaper by it in the middle of the night. Now imagine what that sky brightness does to a survey telescope. These instruments are designed to detect the dimmest possible moving points of light. They would be operating under a sky bright enough to read by. That is the extreme case, and it has happened once in recorded history. But it establishes what the upper end of this interference actually looks like. One more point about forecasting, because it connects the two halves of this story. Both systems I have described share the same fundamental limitation. We can predict where a known asteroid will be years ahead with extraordinary precision. We cannot predict which asteroids exist, because prediction requires prior detection. We can predict when a solar storm will arrive with reasonable accuracy. We cannot predict how severe it will be until it is nearly here. In both cases, the mathematics is excellent, and the inputs are incomplete. That is a specific kind of problem, and better equations do not solve it. It gets solved by better instruments, positioned where the missing information actually sits. For solar storms, that means a monitor further upstream than the current one. Several proposals exist for placing sensors closer to the Sun. Carry that comparison forward, because both halves of this share one flaw. Each would extend the severity warning from under an hour to several hours. For asteroids, it means an infrared telescope positioned sunward of Earth. The same solution applied to a different missing input on a different schedule. So why have I spent this long on space weather in a story about asteroids? Because of what a significant geomagnetic storm does to our ability to see. Part 12. What happens to a telescope when the sky itself starts glowing? Every asteroid survey I described earlier depends on one resource above all others. It is not aperture, or detector sensitivity, or computing power, or funding. It is a dark sky, and that resource is not guaranteed. The faintest object a telescope can detect is governed by contrast, specifically the contrast between the object and the background brightness behind it. Astronomers call the resulting threshold the limiting magnitude of the instrument. Raise the background brightness of the sky and the limiting magnitude drops. Objects near that threshold do not appear dimmer in your images. They stop being distinguishable from the sky at all, which is worse. They simply are not in your data, and no processing recovers them. Now consider what a geomagnetic storm physically does to the upper atmosphere. Charged particles funnel down along magnetic field lines toward the poles. They strike oxygen and nitrogen atoms at altitudes above 100 kilometers. Those collisions excite the atoms, which then emit light as they relax. That emission is what an aurora physically is, at bottom. Green light comes from atomic oxygen at around 100 kilometers altitude. Red comes from oxygen considerably higher up in the thermosphere. Blues and purples come from nitrogen at various altitudes above that. During a strong storm, that emission does not stay confined to a narrow polar oval. The oval expands toward the equator as more energy enters the system. On the 4th of July it reached New Mexico, which is roughly 35 degrees north. During the most extreme historical events, aurora has been recorded in the tropics. Here is the awkward geographic fact that connects these two subjects. Several of the most productive asteroid survey facilities sit at northern latitudes. Catalina operates from Arizona, and the Pan-STARRS survey operates from Hawaii. Both are far enough north that a major storm affects their sky. And wide-field survey work is unusually vulnerable to diffuse sky brightening. These instruments are optimized to detect faint objects across enormous areas. That optimization makes them exquisitely sensitive to exactly this kind of contamination. Radar suffers too, and radar is our most precise orbital tool. When we want a secure orbit for a newly found object, radar is the gold standard. The Goldstone Solar System radar in California is the primary instrument for that work. Radar does more than tell you where an object sits. It measures how fast the object approaches with extraordinary precision. A single radar observation can shrink an orbital uncertainty more than weeks of optical tracking. But radar signals travel through the ionosphere twice, going out and coming back. During a geomagnetic storm, the ionosphere becomes turbulent and unpredictable. That turbulence degrades the measurement precisely when precision matters most. Spacecraft are affected as well, through a mechanism that surprises people. A geomagnetic storm deposits energy into the upper atmosphere, which heats it. There is a third effect, and it reaches into orbit itself. Heated gas expands, so the whole atmosphere physically swells upward. That expansion then increases the air density at satellite altitudes. Higher density means more drag on everything in low orbit. More drag means orbits decay faster, and pointing becomes harder to maintain. Space-based observatories require corrective maneuvers, and those maneuvers cost observing time. So let me now lay out the convergence this story has been building toward. I want to be scrupulous about what it is, and more importantly, what it is not. It is not happening tonight, and I want that clearly understood. Tonight's coronal mass ejection is a minor event by any measure. It will not blind any telescope or degrade any radar measurement meaningfully. What it is a structural vulnerability with two independent clocks running toward it. The first clock is the asteroid detection system I have described at length. It carries a permanent blind spot in the direction of the Sun. It catches many objects with 1 or 2 days of warning. It has catalogued under half the large objects it was legally required to find. The second clock is the Sun itself, running on an 11-year activity cycle. It produces storms whose severity cannot be forecast beyond about an hour. It has already this month exceeded its own forecast by 2 full categories, and during significant events, it degrades exactly the capabilities the first clock depends on. Those 2 systems are entirely unrelated to one another in every respect. There is no causal connection between them of any kind whatsoever. An asteroid does not know what the Sun is doing. The Sun does not know that the asteroid exists at all. And that independence is precisely why the 2 can coincide. Independent processes overlap all the time, because nothing prevents them from doing so. The scenario is not exotic, and it requires no unusual assumptions. A Tunguska-class object approaching through the sunward blind spot, arriving during a period of elevated geomagnetic activity at the survey sites. Sky brightness elevated at the facilities that might have caught it emerging. Neither of those conditions is remotely rare on its own. Objects approach from the sunward direction constantly, as a matter of orbital geometry. Significant geomagnetic storms occur many times during every solar cycle. The probability of overlap in any given week is genuinely low. It is not zero, and unlike almost everything else here, nobody is modelling it. This is a compound risk that falls between 2 separate scientific communities. Picture 2 people searching a dark warehouse, each holding a flashlight. Neither knows the other is there, and occasionally one shines light in the other's eyes. On most nights, nothing at all comes of that arrangement. On some nights, one of them walks straight past something important. I want to be precise about the scale of this interference, because precision matters here. A G1 storm does essentially nothing to astronomical observation at most sites. A G3 storm brightens the sky measurably at northern observatories. A G5 storm, the top of the scale, is a different matter entirely. At those levels, aurora reaches mid-latitudes and stays there for hours. Observatories in Arizona, Hawaii, and Chile would all see degraded conditions. The southern hemisphere sites suffer from the equivalent southern auroral oval. Now, the frequency of severe storms is not evenly distributed in time. The Sun runs on an activity cycle of roughly 11 years. Near the peak of that cycle, severe storms occur multiple times per year. Near the minimum, several years can pass without a single one. We are currently in the declining phase following a solar maximum. That phase is historically when some of the largest storms occur. The Carrington event happened during a similar phase of its cycle, so the interference risk is not uniform, and it is elevated right now. Let me be equally clear about what nobody has actually calculated. I have not found any published analysis combining these two risks. There is no paper estimating the probability of a sunward object arriving during a severe storm. There is no operational protocol for prioritizing asteroid follow-up during space weather events. That absence is not evidence of danger, and I want to state that firmly. It may simply mean the compound probability is small enough to ignore. It may also mean the question falls between two communities that rarely talk. Solar physicists model storms, and planetary defense specialists model orbits. The overlap between those two fields is a handful of people worldwide. Remember the two searchers in the warehouse, each with a flashlight. Neither of those searchers is doing anything wrong at all. Neither of them knows that the other one is there. Hold that image, because I now need to tell you about an object. One that demonstrates both how precise this system can be and how violently its answers move. Part 13. The asteroid whose odds went up because we learned more. On the 27th of December, 2024, an Atlas telescope recorded a moving point of light. The telescope sits at Rio Hurtado in Chile, part of the Last Alert network. The object received the designation 2024 YR4. Follow-up observations placed its diameter between 53 and 67 meters. Tunguska class, precisely the size range this entire story keeps circling. As observations accumulated over the following weeks, the orbit solution produced something unusual. A specific date, the 22nd of December, 2032, carried a non-trivial impact probability, not a theoretical possibility, but a calculated number with real digits behind it. By February of 2025, that probability had climbed to approximately 3.1%, roughly 1 chance in 32 that a city killer would strike Earth. Now I need to explain why that number climbed, because the intuition is backwards. Understanding this is the key to interpreting every asteroid scare you will ever encounter. When you discover an asteroid, you do not know its orbit. You know a handful of positions on the sky, measured over a short interval. From those positions you compute a family of possible orbits. Every orbit in that family fits your observations within their measurement uncertainty. Project that family forward 8 years and it spreads out enormously. The possible positions form a region of space, often millions of kilometers long. It is usually shaped like a stretched ellipse running along the object's path. Astronomers call that whole spread of possibilities the uncertainty region. If Earth happens to sit inside that region, there is an impact probability. That probability is roughly the fraction of the region that Earth occupies. Here is the counterintuitive part, and it is the whole lesson. As you gather more observations, that uncertainty region steadily shrinks. If Earth remains inside a shrinking region, Earth occupies a larger fraction of it. The calculated probability therefore rises rather than falling as you might expect. The probability rising does not mean the asteroid became more dangerous. Nothing about the rock itself changed at any point in that process. It means our uncertainty shrank while Earth stayed inside the remaining possibilities. This is why these episodes almost always end the same way. As the region continues shrinking, one of two things must happen. Either Earth stays inside it, and the probability climbs towards certainty, or the region shrinks past Earth, and the probability collapses to nothing almost instantly. Think of a searchlight beam narrowing across a dark field where you are standing. While the beam is wide, you might be inside it, and you might not. As it narrows, if you are still lit, your odds of being caught rise. Then in one instant the edge sweeps past you and your odds vanish entirely. Keep that searchlight, because I will need it again shortly for a different target. For 2024 YR4, the beam swept past Earth in March of 2025. The impact probability for 2032 dropped to about 0.004%. Earth was ruled out, and the headlines that had built for 2 months evaporated. Now, 2 things happened during that episode that deserve your attention. The first involves the James Webb Space Telescope, which was pointed at the object. Observations were taken in March and in May of 2025. That mattered for a reason specific to how we measure asteroid sizes. Optical telescopes see reflected sunlight, and that creates a fundamental ambiguity. A small bright rock and a large dark rock look identical in reflected light. You cannot separate size from reflectivity using visible observations alone. Infrared observation sees emitted heat instead of seeing reflected sunlight. Heat emission scales with actual surface area, regardless of how reflective the surface is. The infrared measurements from Webb refined the size estimate substantially. They also extended the observation arc, which further tightened the orbit. The second thing that happened is the part most coverage missed entirely. When Earth was ruled out, the shrinking uncertainty region had not swept clear of everything. It was still overlapping something else entirely, and that mattered. The object was still entirely capable of striking the moon itself. Before I follow that thread, I want to give you the tools that professionals use. There are 2 scales for communicating this kind of risk, and they work differently. The first is the Torino scale, which runs from 0 to 10 in whole numbers. It combines impact probability with the energy the object would deliver. 0 means the chance is effectively nil, or the object would burn up harmlessly. 1 means a routine discovery passing near Earth with no cause for concern. Levels 2 through 4 indicate an object meriting attention from astronomers. Levels 5 through 7 indicate a genuinely threatening close encounter. 8 through 10 mean a certain collision, ranging from local destruction to global catastrophe. Almost everything ever discovered sits at 0 on that scale. 2024 YR4 briefly reached level 3 at the peak of the episode. That is the highest any object has reached since the scale was adopted. Apophis reached level 4 for a period in 2004 before being cleared. Notice the design philosophy of that scale, because it is deliberate. Whole numbers only, colour-coded, built to be quoted without being misread. It exists because the alternative is a probability figure in a headline. The second scale is the Palermo scale, and specialists actually use this one. It is continuous rather than integer, and it is logarithmic. It does something more subtle than the Torino scale attempts. It compares the risk from a specific object against the background risk. Specifically, the risk from all the objects we have not found yet over the same period is the clever part, and it admits something important. A Palermo value of 0 means this object carries exactly the background level of risk. Negative values, which describe essentially everything, mean less risk than the unknown population. Positive values mean this object is worse than everything undiscovered combined. Sit with what that scale implicitly concedes about our situation. The entire mathematics is built around a quantity called the background hazard. It assumes a substantial population of objects we have not found. It assumes that population carries a calculable risk we can estimate statistically, and it evaluates every known threat by asking whether it exceeds the anonymous crowd. The professional risk scale in this field has the incomplete catalogue built into its equations. That is not a criticism of the scale, which is honestly designed. It tells you exactly how the people who do this work think about the problem. I want to describe what those 2 months actually looked like from outside, because the public experience of that episode is itself part of this story. In late January of 2025, the probability crossed 1%. That threshold triggers formal notification procedures under standing international agreements. The International Asteroid Warning Network issued its assessment to member agencies. Coverage began cautiously and then accelerated as the number climbed. By mid-February, the figure had reached 3.1%. Watch what happens to the public conversation at this exact moment. Headlines around the world carried a number that most readers could not interpret. 3% sounds small until you attach it to a city. It is roughly the probability of rolling a specific number on 2 dice. It is higher than most people's annual risk of a serious car accident. The Space Mission Planning Advisory Group convened to review deflection options. Analysts examined what could be built and flown before December 2032. 7 years of lead time is genuinely workable for a kinetic impactor. Studies were commissioned, and preliminary mission concepts were sketched out. Then, the probability collapsed, and all of it stopped within days. I want to draw out what that episode demonstrated, because both readings are valid. The machinery worked exactly the way it had been designed to. Detection, notification, coordinated follow-up, telescope time allocation, and public communication. All of it functioned under real pressure with a real candidate. It also revealed how much of the response depended on one advantage. The object was found 8 years before the date in question. Every element of that response required time that a late detection would not provide. Now, there was a second problem visible during those weeks, and it was communication. The rising probability was interpreted almost universally as worsening danger. Very few reports explained that the rise reflected shrinking uncertainty rather than growing risk. That misunderstanding is not the fault of the public at all. It is genuinely counterintuitive, and it took me several paragraphs to explain properly. But it means that the next time this happens, the same confusion will occur. And this will certainly happen again with some other object before long. The searchlight will narrow on something else, and the number will climb. Whether the response is calibrated or chaotic depends on how well this is understood beforehand. Now let me follow up on the thread I left hanging earlier. The searchlight had swept past Earth, and something else was still inside the beam. Part 14. The 4% that vanished in 4 nights of observing. Through the spring of 2025, as the Earth impact scenario collapsed, another number rose. That number was the probability of the object striking the moon instead. The date in question remained the 22nd of December, 2032. In February of 2025, it sat around 1.7 to 1.8%. By the 2nd of April, following the first James Webb observations, it reached 3.8%. Around the 3rd of June, NASA's Center for Near-Earth Object Studies updated it again. That update combined Webb's near-infrared camera data with ground-based observations. The analysis team was led by Andy Rivkin of the Johns Hopkins University Applied Physics Laboratory. The revised figure came out at 4.3%. 4.3% chance that a 50 to 67 meter asteroid would hit the moon. On a specific date, 7 years in the future, calculated from a telescope in Chile. That number circulated widely, and I have seen it quoted repeatedly over the past year. It is no longer current, and the correction is the entire point of this part. In February of this year, 2026, Webb observed the object again. Observations were taken on the 18th and again on the 26th of that month. On the 5th of March 2026, NASA published the revised assessment. The probability of a lunar impact is now 0.005%. That works out to roughly 1 chance in 20,000. the asteroid is now expected to pass approximately 21,200 kilometers from the lunar surface. NASA's own language was that lunar impact is no longer a possibility, from 4.3% to 0.005%, on the strength of 4 additional nights of observation with the right instrument. That is the searchlight sweeping past, exactly as I described it, and there are 2 lessons inside it that point in opposite directions. Weigh these 2 conclusions against each other as I give them. The first lesson is genuinely reassuring, and I want to state it clearly. The system works, and it works extremely well when given time. Given sufficient observations with capable instruments, orbit determination converges beautifully. We took an object first seen as a smudge on a Chilean telescope. Within roughly 14 months, we established its position 8 years ahead, to within a few thousand kilometers at a distance of hundreds of millions. That is one of the more impressive things this species routinely does. It is worth pausing on before I take it away from you. The second lesson is the uncomfortable one, and it undercuts the first. Every bit of that convergence depended on the object being found in December of 2024. That discovery came 8 full years before the date in question. 8 years of lead time is what made all of it possible. 8 years of observation arcs, of Webb telescope time, of orbital refinement. 8 years for the searchlight to narrow and sweep clear. 2026 OX3, 3 days ago, gave us roughly 36 hours. 2019 OK gave us 24 hours of warning. Chelyabinsk gave us nothing whatsoever, not even a single minute. The precision of this system is extraordinary, and the coverage of this system is incomplete. Those 2 statements do not contradict each other in any way. We are superb at answering questions about objects we already know about. The entire problem lives inside the objects we have never seen. I should tell you what a lunar impact would have meant, because it was studied seriously. Estimates put the energy release at around 6.5 megatons of TNT equivalent. It would have formed a crater roughly 1 kilometer across on the lunar surface. The flash would likely have been visible from Earth without a telescope. Seismometers left by the Apollo missions would have registered a substantial moonquake. There was genuine and unresolved scientific debate about the ejector. A lunar impact throws material off the surface at high speed. The moon's gravity is weak, so some of that material escapes entirely. Whether enough would reach cislunar space to threaten satellites was disputed. By 2032, crude lunar infrastructure may well exist there. That debate is now moot for this one particular object. It will not be moot forever, and the next candidate is a matter of time. 2024 YR4 becomes observable again in 2028. Astronomers will look at it once more, because that is what they do. Look closely at how that final answer was actually obtained. There is something worth noting about the instruments that resolved this. The James Webb Space Telescope was not built for planetary defense in any sense. It was designed to observe the earliest galaxies in the universe. Time on that telescope is among the most contested resources in science. Proposals compete fiercely, and allocation committees reject most of them. Diverting it to track a single asteroid required a specific justification. That justification existed because the probability was non-trivial and the object was faint. Webb could measure it in infrared when ground telescopes could barely see it at all. But notice the dependency involved, because it is genuinely fragile. Our best measurement of a potential impactor came from an instrument built for cosmology. There is no dedicated telescope whose primary job is characterizing threatening objects. When something appears, we borrow time from instruments designed for other purposes. Now consider what happens when 2 candidates appear in the same year, or when a candidate appears during a period when Webb's schedule is fully committed. The system has no redundancy. because it was never designed as a system. Let me also address the lunar impact question with more care. Some scientists argued a lunar impact would have been scientifically valuable. We would observe a fresh impact of known size and known velocity. Every crater we study is millions of years old and eroded by micrometeorites. A new one, formed on a known date, would calibrate an enormous amount of geology. The Apollo missions left seismometers on the lunar surface that operated for years. Modern equivalents would have recorded the impact in extraordinary detail. We would learn how seismic energy propagates through the lunar interior. Against that, the ejector concern was real and remains unresolved. Material thrown off the moon at sufficient speed does not fall back. Some of it enters orbits that cross the region where satellites operate. Estimates of how much varied by orders of magnitude between studies. That disagreement was never settled because the question stopped being urgent. It will become urgent again, on a date nobody has calculated yet. Stay with me, because there is a category of object I have not addressed yet. These are not rocks that we simply failed to find. These are rocks that we found once and then lost. Part 15. The rocks we found once and then misplaced. There is a category in this field called lost asteroids, and the name is literal. These are objects that were detected, catalogued, and then could not be found again. Here is exactly how an object becomes lost, and the mechanism is mundane. A survey telescope detects it and reports the observations to the Minor Planet Center. That organization is the International Clearinghouse for Astrometry from observatories worldwide. It assigns provisional designations and computes preliminary orbits from whatever data arrives. The object gets a name and appears in the database, and then it moves out of range, or the weather closes over the observatories, or the moon rises and washes out the sky for a week, or nobody could schedule follow-up time on a large enough telescope. The observation arc closes at a few days, or sometimes a few hours. The resulting orbit carries so much uncertainty that its future position is unclear. When it comes back around, nobody knows where in the sky to point. That is the whole mechanism, and it is a scheduling problem more than a science problem. It happens constantly, and it is one of the quiet failures of this field. Recall the condition code I mentioned for the rock from Monday. That figure was 7 on a scale running up to 9. That number is a direct measure of how confidently we could find it again. A short arc object with a high condition code is a candidate for becoming lost. Most lost objects are small, and many are eventually rediscovered years later. Sometimes they receive a new designation before anyone realizes they are the same rock. This is ordinary science, and it is not a scandal by any measure. But notice the shape of the failure, because it repeats throughout this entire story. The bottleneck is not detection, and it never really was. The bottleneck is follow-up, which is a far duller problem. It is having enough telescope time on enough nights pointed at the right places. Converting a detection into a secure orbit takes more resources than making the detection. We are considerably better at finding things once than at keeping track of them, and there is a physical process that makes long-term tracking harder still. It is genuinely elegant, and it is called the Yarkovsky effect. An asteroid rotates continuously as it orbits around the Sun. The side facing the Sun heats up during its day, but it does not radiate that heat away instantly, because materials have thermal inertia. You experience that same thermal lag on every summer afternoon. The Sun is highest at noon, but the hottest part of the day comes later. Heat accumulates faster than it escapes, and the peak lags behind the input. So an asteroid's warmest region is not the point directly facing the Sun. It is a region rotated somewhat past that point on the afternoon side. Now, radiating heat means emitting photons, and photons carry momentum. An object radiating more strongly from one side experiences a tiny push the other way. The asteroid is therefore being continuously pushed by its own waste heat. Give this effect your attention, because its size is deceiving. The force is almost unimaginably small, far less than a person's breath, but it acts constantly in the same direction for millions of years. Over those timescales, it moves an asteroid's orbit by a substantial amount. This is not an academic curiosity, and it has real consequences for prediction. For high-precision impact forecasts decades ahead, Yarkovsky must be modelled explicitly. Doing that requires knowing the object's rotation rate and its shape. It requires knowing its surface thermal properties and its axial tilt, all of which require close observation with instruments we have limited access to. Let me put that as simply as I possibly can here. An asteroid's future is not determined by gravity alone, it turns out. It is also being steered, very slightly, by the heat it radiates. To know where it is going, you must know what it is made of. Now let me address where these objects come from, because the answer explains the population. The near-Earth population is not permanent, and that fact surprises most people. Objects do not remain in Earth crossing orbits for the age of the solar system. Those orbits are unstable when measured over long enough periods. The objects get perturbed by close encounters with the planets. They collide with something else, or they are broken apart. They fall into the sun or get ejected from the system entirely. The typical lifetime of a near-Earth asteroid is a few million years. That sounds enormous until you compare it against 4.5 billion. It means the entire near-Earth population turns over roughly 1,000 times. So the population must be continuously resupplied from somewhere, and it is. The source is the main asteroid belt between Mars and Jupiter. The delivery mechanism involves orbital structures called the Kirkwood gaps. Here is what those are, and the physics is beautifully simple. Jupiter is enormously massive, containing more mass than all other planets combined. An asteroid orbiting at certain specific distances completes orbits in simple ratios to Jupiter's. 3 of its orbits for every one of Jupiter's, for instance. At those distances, the asteroid receives a gravitational tug at the same orbital position repeatedly, the same push, at the same point, cycle after cycle, in phase. It is the same principle as pushing a child on a swing. One small push at a random moment does almost nothing. The same push delivered at exactly the right point every cycle builds enormous amplitude. Timing alone converts a trivial force into an enormous effect. Over millions of years, those resonant tugs stretch the asteroid's orbit progressively. Eventually, the orbit crosses the paths of Mars and then Earth. Picture the belt itself for a moment as I describe it. Plot the distances of main belt asteroids, and you see actual gaps at those resonances. Those gaps are not empty because nothing formed there originally. They are empty because everything that formed there was eventually thrown elsewhere. And a fraction of elsewhere is here, in our neighbourhood, permanently. Remember the swing. Because it explains something about timescales that matters. The delivery of new near-Earth objects is continuous and steady. There is no burst, no wave, no recent change in the supply rate. The system has been running at roughly this rate for billions of years. Which means the answer to the question everyone asks is a firm no. There is no pattern of increasing danger, no cluster, no recent shift. Currently around 38 to 41,000 near-Earth objects are known. The estimated total asteroid population in the solar system exceeds 1 million. The sky above us has not changed in any way. Our eyes have improved, and the improvement is both recent and partial. I want to be clear that this is the honest answer, even though it is duller. A rising threat would be a better story, and it would be false. The traffic is constant, and the map is incomplete, and only one of those is fixable. The Yarkovsky effect has been measured directly, and Bennu is the best example. OSIRIS-RX tracked that asteroid for over 2 years at close range. Bennu's orbit is drifting by roughly 280 meters per year. That drift is caused entirely by the thermal push I just described. 280 meters sounds trivial against a solar orbit of billions of kilometers. Now project that drift forward across longer spans of time. Over a century, that becomes 28 kilometers of accumulated displacement. Over a full millennium, it becomes 2,800 kilometers of drift. Over the timescales relevant to long-term impact prediction, it dominates the uncertainty. Bennu matters for a specific reason beyond the physics demonstration. It has a small but non-zero probability of striking Earth in the 22nd century. The relevant date is in September of 2182. Note that date, because it is further out than any other in this story. The probability is around 1 in 2700, which is small but calculable. That number is only calculable because OSIRIS-RX measured the Yarkovsky drift directly. Without that measurement, the uncertainty would swamp any prediction that far out. We know Bennu's future better than any other asteroid because we visited it. Hold that comparison against the 14,000 objects nobody has ever observed. We have precise century-scale predictions for the handful we have visited. We have rough estimates for the tens of thousands we have merely catalogued. And we have nothing at all for the majority that remain undiscovered. Let me give you one more figure about the lost object problem. The Minor Planet Center's database contains a substantial number of single apparition objects. These were observed during one approach and never recovered afterward. Some will be rediscovered eventually and matched to their old designations. Others are functionally gone until they happen to pass close again. Every one of those represents work already done, and then wasted. Telescope time was spent, observations were taken, an orbit was computed, and then the object slipped past the follow-up capacity of the network. This is the least dramatic failure in this entire story, and possibly the most consequential. It is not a failure to look in the first place. It is a failure to go back and look a second time. But there is one more thing we need to know about these objects. Not where they are, or where they are going, but what they actually are, because that determines whether we could move one at all. Part 16. Why what the rock is made of decides whether we can move it. There is a question I have deferred until now, and it turns out to be decisive. What is an asteroid actually made of, in structural terms? Is it a rock, in the way a boulder is a rock? For most of the 20th century, the assumption was the obvious one. A small asteroid is a monolithic piece of stone or metal. It would be a fragment chipped off something larger, solid throughout. That assumption is now known to be wrong for much of the population. The correction came from two directions, and both were expensive to obtain. The first was radar imaging, which reveals shape and rotation from a distance. The second was actually going to these objects and touching them. When Japan's Hayabusa 2 mission arrived at the asteroid Ryugu, it found something unexpected. When NASA's OSIRIS-RX mission arrived at Bennu, it found the same thing. These objects are not solid bodies in any meaningful sense. They are aggregations of many smaller pieces, loosely bound together. Loose collections of boulders, gravel, and dust held together weakly. The binding forces are their own feeble gravity and cohesion between grains. The field calls them rubble piles, and the name is accurate. Bennu delivered a genuine surprise that changed how people think about these objects. The single most telling detail came from the sampling attempt itself. When OSIRIS-RX touched the surface to collect a sample, it did not bounce. The surface offered almost no resistance, and the spacecraft sank into it. The team described material behaving like a pit of loose grains with negligible cohesion. Had the thrusters not fired to back away, assessments suggest it would have kept sinking. Now apply that finding directly to deflection, and the implications become concrete. If you strike a solid monolith with a kinetic impactor, the physics is relatively clean. Momentum transfers, some material is excavated, and the velocity change is predictable. If you strike a rubble pile, the outcome becomes much harder to forecast. The impactor may bury itself deep inside the loose structure. The whole body may absorb and redistribute the energy internally, or the ejector plume may be enormous, as it was at Dimorphos. Recall the sand pile from earlier, and now you can see why it mattered. DART overperformed its success criterion by a factor of 27. The reason is that it hit something loose and threw material backward at speed. So being loose turned out to be helpful in that specific case, but it was helpful by an amount nobody could have predicted in advance. The uncertainty in beta, from 2.2 to 4.9, follows directly. We do not know the internal structure of what we hit. That is exactly the question HERA begins resolving in November. There is also a category of object that is not loose at all. Radar is how we tell the difference, and one recent example is instructive. In July of 2025, an object designated 2025 OW passed Earth. It came within about 1.6 lunar distances of this planet. It had been discovered on the 4th of July that year by Pan-STARRS 2 on Haleakala. That discovery gave several weeks of lead time rather than several hours, which meant it could be studied properly rather than merely logged. Goldstone radar imaged it and produced measurements that surprised the observing team. The object measured roughly 60 meters across, placing it squarely in Tunguska class, and that object was rotating extraordinarily fast on its axis. One full rotation every 1.5 to 3 minutes. That rotation rate is the diagnostic, and it rules out one whole category. A rubble pile cannot spin that fast and remain assembled. At those rates, the centrifugal effect at the surface exceeds the object's own gravity. Any loose material would simply lift off and drift away. Hold on to that spin rate, because it settles an old argument. So an object rotating once every 2 minutes must have real internal strength. It is a solid body, held together by material cohesion rather than gravity. It is a rock, in the way a boulder is a rock. And a solid body responds to a kinetic impactor very differently. Less ejector means lower beta, which means a smaller push. The same spacecraft delivers a fraction of the velocity change, which means that if a threatening object appeared tomorrow, one question becomes urgent immediately. Not only where it is going, but what it is and how fast it spins. That single measurement tells you whether our one validated technique will work. Radar answers that question, and radar carries a hard constraint. Signal strength falls off with the fourth power of distance. Double the range and you need 16 times the sensitivity to see the same object. So planetary radar cannot survey, and it cannot find anything on its own. It can only characterize objects that optical surveys have already located, and only during the narrow window when those objects are close. There is one more thing radar gives us that nothing else can. It measures rotation, and rotation tells you about the object's history. A slowly tumbling body has probably not been disturbed for a long time. A fast rotator has usually been spun up by sunlight over millions of years. That process is a cousin of the Yarkovsky effect I described earlier. The same thermal photons that push an orbit can also spin a body. So a single radar session tells you size, shape, spin and structure. It tells you whether a kinetic impactor would work well or poorly. It tells you whether the object is likely one piece or many. All of that from an object we can only observe when it is already close. Every capability in this field stacks on top of detection. Radar needs a target that somebody else has already found. Deflection needs an orbit that somebody else has already calculated. Warning needs a prediction built on observations that somebody scheduled. When you build a tower like that, the failure mode is always at the bottom. Which brings me to the instrument designed to fix the bottom of that tower. Everything I have described about the sunward blind spot has one clean solution. The people in this field have known exactly what it is for over 20 years. Put the telescope in space and make it observe in infrared. Both halves of that sentence are doing real work, so take them separately. Getting above the air solves the atmospheric problem completely and permanently. There is no scattered daylight in vacuum, because there is no air to scatter it. A spacecraft positioned correctly can observe regions of sky permanently denied from the ground. Infrared solves the phase problem, which is the subtler of the two. An object approaching from the sunward direction shows us mostly its unlit side. In visible light, it is a dark crescent against a bright background, but an object being heavily illuminated by the sun is also being heavily heated. Heat radiates in all directions regardless of which side faces us. In the infrared, a sunward asteroid is not a dark crescent at all. It is a warm object glowing against a genuinely cold sky. That mission already exists on paper, and it is called NEO-Surveyor. It carries a 50cm aperture telescope with 2 infrared detection channels. One channel covers 4 to 5.2 microns of wavelength. The other covers 6 to 10 microns, which captures cooler and more distant objects. Together they measure both position and thermal emission, which yields real size estimates. It will be stationed at the first Lagrange point, 1.5 million kilometers sunward. That is the same neighborhood where the solar wind monitors sit. From there it can look toward the inner solar system in ways no ground telescope can. Its launch mass is around 1,300 kilograms, and it flies on a Falcon 9. Its baseline survey runs 5 years and carries a specific target. It aims to find 2/3 of undiscovered objects above 140 meters. Now here are the dates, and this is where the story becomes about budgets. The mission was originally targeted for launch in 2026, which is this year. It is not launching this year, and that fact carries consequences. In 2022, NEO-Surveyor absorbed a budget reduction of more than 30%. The schedule slipped accordingly, as schedules do when funding is cut mid-development. Total mission cost grew from around $1 billion to roughly $1.6 billion. That growth pattern is worth understanding, because it is not waste in the usual sense. Pay attention to this pattern, because it repeats across every delayed program. Stretching a project's timeline increases its cost, because teams must be retained longer. Cutting a budget by 30% frequently increases the total spent. As of May this year, the Jet Propulsion Laboratory stated the current position. Launch is set for no earlier than September of 2027. Teams across the United States are building components, and the spacecraft is in integration and testing. That phrase, no earlier than, is standard aerospace language, and it means precisely what it says. It is a flaw, not a commitment, and flaws have moved before. Then there is the completion timeline, which is where the arithmetic becomes uncomfortable. Amy Mainzer, the mission's principal investigator, testified before the House of Representatives. In that testimony, on the 12th of May, 2025, she addressed the 90% goal. Reaching it would take roughly 10 to 12 years following launch. Do that calculation along with me for just a moment. Launch happens no earlier than September of the year 2027. Then add 10 to 12 years of survey operations after that. That places completion somewhere between 2037 and 2039. The mandate was written in 2005 with a deadline of 2020. completion would arrive 17 to 19 years past that legal deadline. It would arrive 32 to 34 years after the law was passed. The European Space Agency is developing its own answer to the same problem. The mission is called NEOMER, an infrared space telescope aimed at the sunward blind spot. It is the European version of closing exactly the same gap. And on the ground, Vera Rubin continues to transform the discovery rate. It cannot solve the sunward problem, because it sits under an atmosphere. It can substantially reduce the follow-up problem, which matters enormously. Now let me lay out where this goes from here. Honestly, there are two plausible trajectories, and the difference is decided in budget documents. In the first trajectory, NEO Surveyor holds its window or slips modestly. It reaches the first Lagrange point and begins surveying in infrared. Rubin continues ramping up, adding thousands of objects annually and securing their orbits. The NEOMER mission proceeds steadily through its own development phase. Hera arrives in November and converts the deflection uncertainty into engineering data. Under that path, the 90% catalogue is achieved in the late 2030s. The sunward blind spot narrows substantially, though it never closes completely. Warning times for city killers improve from days to years for much of the population. That is not fantasy, and every element of it is currently funded or in flight. It is the default outcome if nothing further goes wrong. In the second trajectory, the pressure on science budgets continues. NEO Surveyor slips again, as it has already slipped once. Follow that second path with me now, item by item. Staffing at the coordination office remains at roughly one civil servant and one contractor. The observation program budget stays flat, which means it shrinks in real terms annually. Rubin still performs well, because Rubin is already built and operating, but the follow-up capacity to convert its detections into secure orbits does not scale with it. The number of found and lost objects climbs rather than falls. Under that path, the 90% goal recedes past 2040. The blind spot stays open, exactly as it is tonight. The practical warning time for a sunward object remains what it always was. So which of those two trajectories does the current evidence actually support? I will give you the most honest reading rather than the most dramatic one. The evidence sits between them and is drifting slowly toward the second. NEO Surveyor has already absorbed one substantial cut and one multi-year delay. Its cost has grown in the pattern typical of a project being stretched. A Government Accountability Office assessment found NASA shed roughly 4,000 civil servants during 2025. That assessment confirmed impacts across 25 of 36 major projects, including this one. A proposed 23% reduction to NASA science for fiscal year 2027 is in play. Against that, Rubin is genuinely transformative and it is already operating. Hera is running ahead of schedule and arrives within months. And the 2024 YR4 episode showed the international apparatus functioning under pressure. So the honest forecast is mixed, and both trends are running simultaneously. Detection capability is improving faster than at any point in history. Institutional capacity to sustain that improvement is under real strain. Which one dominates over the next decade is not a scientific question at all. I want to give you one specific thing to watch over the coming year. Not announcements, not renderings, not press releases about the mission. Watch the launch date, and nothing else about the mission. It moved from 2026 to no earlier than September 2027. If it moves again, that tells you which trajectory this is on, and it tells you long before any consequence becomes visible to anyone. Part 17. The rock that passed on Monday, and the ones still out there. Let me take you back to where this started. 3 days ago, 2026 OX3 passed within 249,000 kilometers of this planet. It was 10 to 23 meters across, moving at 9.45 kilometers per second. We had known that it existed for roughly 36 hours. Bring those opening numbers back into focus one final time. 2 days before that, 2026 OD3 came closer still. Tomorrow, 2026 OS passes at around 3 lunar distances. We are uncertain about its arrival time by roughly 21 hours in either direction. Not one of those objects was ever going to hit us. Every one of them was, in the language of the agencies, routine. I hope the word routine reads differently to you now than it did earlier. Routine does not mean handled, or solved, or under control. It means frequent, which is a very different claim about the world. This is the ordinary operating condition of a planet in an unswept solar system. The events I have described are not warnings that something is coming. They are the constant background against which something will eventually happen. So here is the question I opened with, and I am not going to resolve it. How many objects large enough to erase a city are moving through this neighbourhood uncatalogued? The statistical estimate says thousands, based on the population models. The catalogue says we are found under half of the larger class. It says we have no mandate at all covering the smaller and more frequent one. The gap between those two figures is the answer, and nobody can narrow it further tonight. What I can tell you is what would change that number, because those things exist. An infrared telescope at the first Lagrange point, currently in a clean room. A European mission designed for the same blind spot, still in development. A survey observatory in Chile already finding thousands of objects nobody knew about. A spacecraft arriving at a small moonlet in November to check our only deflection. Those are real programs, built by real people, on budgets that are currently contested. And there is one thing I keep returning to. From the coldest morning in this story. 1,500 people were injured at Chelyabinsk in 2013. Almost every one of those injuries came from ordinary window glass. Almost every one of those people was at a window because they saw a flash. The gap between the light and the shockwave was roughly 2 minutes. 2 minutes is not enough time to evacuate a city. It is more than enough time to step away from a window. The most effective response available for the most common dangerous event is not a spacecraft. It is a message delivered fast enough, telling people where not to stand. That is unglamorous, and it has no rocket in it, and it works. It also requires the one thing this entire story has been circling. It requires knowing, which requires seeing, which requires an instrument pointed the right way. Here is what makes this particular subject so difficult to sustain attention on. It has no deadline attached to it anywhere at all. An earthquake generates coverage for a week, and then the coverage ends. A hurricane holds attention for exactly as long as it is over land. Every disaster comes with a built-in news cycle that rises and falls. Consider why this subject behaves differently from every other one. That is usually fine, because the event finishes and the danger passes. This one never finishes, and it never spikes into urgency either. There is no moment when asteroid detection suddenly becomes urgent. There is only the moment when urgency stops being useful, and that moment arrives without notice. Consider the gap in the catalogue and the launch date that keeps moving. Consider an office running on an acting appointment for over a year. None of that reflects anyone deciding this subject does not matter. It reflects nobody ever having to decide, because the decision could always wait. Until a year arrives when it could not have waited, and by then the decision is historical. Let me leave you with one last piece of arithmetic. Between the 24th of July and the 1st of August, 8 objects passed close enough to log. 2 of them came inside the orbit of the Moon. 2 of them were large enough that an impact would have been a national emergency. Not one of those 8 was known to exist a year ago. Several of them were not known to exist a week ago. Next week there will be another set of them entirely, and the week after that, and every week for the rest of your life. That is not a prediction, and it is not a warning. It is a description of the ordinary condition of living here. 3 days ago a rock passed between us and the moon. We had known about it for roughly 36 hours by then. Almost nobody noticed, and nothing happened, and that is the most likely outcome. It is also precisely what the week before a different outcome would look like. The next one is already out there, on an orbit that was fixed millions of years ago. Whether we see it coming depends entirely on what we build between now and then.